Tá, então, gente, a gente deve estar no ar com um vídeo filler. Ok. Acho que estamos live.
It definitely changes your life. It helps you establish relationships that are really tighter because you already have a lot of things in common in the way you think, work, want to change the world around you.
As you get involved in IEEE, you really get a sense that you want to give back and to grow the community that you have.
I think there's a natural intersection between IEEE and its role in promoting the emergence of new technologies and entrepreneurship.
Channel to get to connect with professionals in the field. You never know what's going to happen when you meet so prominent people that are foreseeing the future.
What has IEEE brought me? I've worked full-time in power system automation, which we call smart grid, for over 41 years now, full-time. And the job changes I've made were through industry friends that knew of opportunities that I wouldn't have known otherwise and opened up the door for me. And many of these industry friends I met through IEEE.
What other place can you try to take a risk of doing our presentation skills and bringing in somebody from industry to talk to other scientists and engineers? I've been a member of IEEE for 25 years, and I still talk and mentor about this to this day.
IEEE has given me opportunities to network in terms of getting to know the leaders in the field, and also has provided an outlet for those leaders to know what I'm doing. So it's been good for both of us.
Given the world that we're living in now, where everything is pretty much about the internet and about connectivity, it's actually a good time to be an engineer and to be a telecommunication and networking engineer.
We know it's about the dynamics between people and people groups where our future is. And engineers can facilitate that, but they don't have the answers. It's the answering of us together as a community, not as engineers alone. So engineering is not going to solve the world, but it's going to facilitate that problem solving and getting together.
At IEEE, we believe technologists are the key drivers of tomorrow's innovations because we can really do what IEEE's motto states. We can advance technology for the benefit of humanity.
I always wanted my education to mean something more than just, doing a day job that pays my checks. I wanted to see how my background in engineering and other things could have an impact that can make somebody's life better.
Being able to connect our members with younger students and engaging them to emphasize that it is important, that what they are pursuing in their STEM careers is truly going to be the next thing that affects all of humanity, because all technology that we make is affecting people, and it's not just IEEE members, it's everybody.
Tá bom, sim. Erik? Let me just quickly explain to Erik how it's going to work.
It definitely changes your life. It helps you establish relationships that are really tighter because you already have a lot of things in common in the way you think, work, want to change the world around you.
As you get involved in IEEE, you really get a sense that you want to give back and
so the idea is to have you here.
I think there's a natural intersection between IEEE and its role in promoting the emergence of new technologies and entrepreneurship.
IEEE was a great channel to get to connect with professionals in the field. You never know what's going to happen when you meet so prominent people that are foreseeing the future.
Erik, are you ready?
What has IEEE brought me? I've worked full-time in power system automation, which we call smart grid, for over 41 years now, full-time. And the job changes I've made
also
were
your
through industry friends
So as soon as you appear where we are right now, you will be live for everyone on YouTube.
Many of these industry friends I met through IEEE.
What other place can you try to take a risk of doing a
You
presentation
can do whatever you want. You can
bringing
do it
in
now,
somebody
you
from
can do it in
industry
an
to talk to
hour,
other
but it
scientists
has
and
to be shared
engineers? I've been a member of
before
IEEE
you
for
go into
25
swing,
years, and
right?
I still talk and mentor about this
And
to this day.
IEEE has given me opportunities to network in terms of
Perfect.
getting to
Yeah,
know the
that's
leaders
right.
in the field, and also has provided an outlet
So
for
it's kind of
those
like
leaders to know what I'm
a
doing. So,
live presentation,
it's been,
like a
good for both of
face-to-face
us.
presentation.
Given the world
Right,
that we live
everyone
in
is
now,
seeing
where everything
everything,
is pretty much about the internet and about
does not apply
connectivity,
for the first talk.
it's actually a
The
good
first
time
talk
to
we
be
have time to set up and
engineer and to be a
everything, but the
telecommunication
second
and
talk
networking engineer.
is
We know it's about the
like
dynamics between people and people groups
seemingly
where a few
integrated into the
engineers can
life.
facilitate that, but they don't have the answers. It's the answering of us together as a community, not as engineers alone. So engineering is not going to solve the world, but it's going to facilitate that problem solving and getting together.
No, not really,
At
Charlie.
IEEE,
No.
we believe technologists
I'm going to introduce you and Erik's
because
screen.
we can really
So,
do what IEEE
let me just show you an example
We can
here.
advance
So,
technology for
let's
the
suppose
benefit
that
of humanity.
that
I always
this
wanted my
thing
education
here
to be
is
something more
Erik's,
than just,
right?
doing a day job.
Live
Checks.
will be
I wanted to see
Amara
how
will
my
be
background
Move,
in
Pace,
engineering and
and
other
myself.
things would have an
So
impact
it will
that
be
can
something like
make
this,
people's lives
right?
better.
Being able to
Let me just put
connect
everyone back.
our
And
members
when
with
you're
other
not on
students and
stream,
engaging
then you
them
cannot
to
talk
emphasize
anything.
that it
You
is
will
important,
be
that what they are
automatically
pursuing
muted,
in their
right?
STEM careers is truly going to be the next thing that affects all of humanity, because all technology that we
No,
make
not yet.
is affecting people, and it's not just IEEE members, it's everybody. It definitely changes your life. It helps you establish relationships that are really tighter because you already have a lot of things in common in the way you think, work, want to change the world around you.
As you get involved in IEEE, you really get a sense that you want to give back and to grow the community that you have.
I think there's a natural intersection between IEEE and its role in promoting the emergence of new technologies and entrepreneurship.
IEEE was a great channel to get to connect with professionals in the field. You never know what's going to happen when you meet so prominent people that are foreseeing the future.
What has IEEE brought me? I've worked full-time in power system automation, which we call smart grid, for over 41 years now, full-time. And the job changes I've made were through industry friends that knew of opportunities that I wouldn't have known otherwise and opened up the door for me. And many of these industry friends I met through IEEE.
What other place can you try to take a risk of doing your presentation skills and bringing in somebody from industry to talk to other scientists and engineers? I've been a member of IEEE for 25 years, and I still talk and mentor about this to this day.
IEEE has given me opportunities to network in terms of getting to know the leaders in the field, and also has provided an outlet for those leaders to know what I'm doing. So it's been good for both of us.
Given the world that we're living in now, where everything is pretty much about the internet and about connectivity, it's actually a good time to be an engineer and to be a telecommunication and networking engineer.
We know it's about the dynamics between people and people groups where a few
speak about PG
and
Micro,
engineers can facilitate
and
it, but
then
they
I will
don't have
call
the
you
answers. It's
to
the
speak about
answering of
CASSW,
us together as a
and
community,
then
not as engineers
Ricardo
alone.
about
So engineering is
Region
not going
9,
to solve the world, but it's going
and
to facilitate
Ricardo will then call Fabio
that
to
problem
talk about the
solving
poster session.
together.
That's fine
At
with you.
IEEE, we believe technologists are the key drivers of tomorrow's innovations because we can really do what IEEE's motto states. We can advance technology for the benefit of humanity.
I always wanted my education to mean something more
Nice to
than
see you,
just doing a day job that pays my checks. I wanted to see how my background in engineering and other things could have an impact.
Yes,
that can make
the
somebody's
time
life
slot
better.
is
Being
starting
able
in
to
2 minutes,
connect
and we have 20
our
minutes for the open.
members with
So
younger students and
we
engaging
should be
them
ready in
to
22 minutes.
emphasize that it is important, that what they are pursuing in their STEM careers is truly going to be the next thing that affects all of humanity, because all technology that we make is affecting people, and it's not just IEEE members, it's everybody.
We will remove you from the live. Oh, Massimo's here. Awesome. Okay. Let me have Massimo. Hello, Massimo.
It definitely changes your life.
Massimo, you
It
can
helps you
try
establish
sharing your screen
relationships
already.
that are really tighter, because
then we can
you
pass it
already
here.
have a lot of things in common in the way you think, work,
Yes.
want to
Let me add it to
change
the
the
screen,
world
so
around
it
you.
will be like
As you
this.
get involved in IEEE, you really get a sense that you want to give back and to grow the community that you have.
I think there's a natural intersection between
It's on your camera, Massimo,
including
that
emerging new technologies
we seem to be
and
watching
entrepreneurship.
your
IEEE was a great channel to get to connect with professionals in the field. You never know what's going to happen when you meet so prominent people that are foreseeing the future.
Yeah, there you go.
What has IEEE brought me? I've worked full-time in power system automation, which we call smart grid, for over 41 years now, full-time. And the job changes I've made were through industry friends that knew of opportunities that I wouldn't have known otherwise, and open up the door for me. And many of these industry friends I met through IEEE.
No, you can leave it.
What other place
leave it,
can you
Massimo.
try
You can
to
leave your
take a
screen
risk
as well,
of doing our
because I can
presentation
remove
skills
you.
and bringing in somebody from industry to talk to other scientists and engineers? I've been a member of IEEE for 25 years, and I still talk and mentor about this to this day.
IEEE has given me opportunities to network in terms of getting to know
Yes,
the leaders
so
in the
guys,
field,
I will
and
start
also has provided an
removing
outlet
you from the
for those
feed.
leaders to know what I'm doing.
So, Massimo,
it's been
Bunty, I removed
good
you
for
too.
both of us.
Given the world
and
that we live
also
in now,
Erik.
where everything is pretty much about the internet
Yes,
and about
the rest stays
connectivity,
here for the panel.
it's actually a good time to be
And now
an
I will hit
engineer
the
and to
button
be
to
a
go
telecommunication
live,
and
and I'll
networking
let you know
engineer.
as
We
soon
know
as
it's
you're
about the
live.
dynamics between people and people groups where our future is. And engineers can facilitate that, but they don't have the answers. It's the answering of us together as a community.
By welcoming all our attendees, our associates in IEEE and CAS. We have a great event in the next 4 days. So this is the first time that our CAS workshop will be virtual. So we have a great program. Ricardo will talk about it in a few minutes. So I would also like to thank our committee who organized this this great event. We've been organizing for a few months already. So in our opening panel, we have here Thiago Balin from PG Micro. He'll say a few words about the program. And then Amara, who's the president of CASSW. And then Ricardo, who's on the BOG of Region 9. And then finally, Fabio is also here to give a few words about the poster session. So Thiago, if you please.
Okay, thank you, José. In the name of the graduate program on microelectronics from Federal University of Rio Grande do Sul, we welcome everybody to this 10th edition of the IEEE Circuits and Systems Rio Grande do Sul workshop. We also thank all the speakers on the organizing team, and we hope you have an excellent workshop and can enjoy this initiative of our team of professors. PG Micro is very active in IEEE activities, and the organizing and the coordinating committee of PG Micro also supports this kind of activity. So once again, we thank all you speakers and all the organizing team for this excellent program you are giving in this edition of the CASSW Rio Grande do Sul workshop. Okay, thank you.
Thank you, Thiago. Amara, thank you for being here. So if you would like to say a few words.
Okay, thank you very much for inviting me to participate in this opening of your summer school. As you all know, we are living a situation that we had not seen in the last decades, and which prevent us from traveling and from meeting friends, attending conferences, and so on. I would have gladly made the trip to participate in this event. Despite the situation, CASSW has shown extreme agility to adapt and successfully continue its activities. I could mention the organization of our conferences in hybrid or virtual format. I hope that you all attended ISCAS, who was for the first time held virtually. The organization also of our distinguished lectures in a series of webinars, 3 webinar series. The launch of the Africa Initiative, our response to COVID-19 through the organization of 2 competitions. The first one is the COVID-19 student design competition, and the second one is the COVID-19 entrepreneurs competitions, whose success exceeds really our expectations. So to ensure the continuity of our activities, regardless of changes in the governance of our society, we have worked collaboratively on the development of a 2020-2024 strategic plan that you can that is posted in our website. You can consult it or download it. We have in this strategic plan, we have revised our mission and vision, established values to guide our behavior as members and as organization. We defined some strategic directions globally and technically. I really strongly encourage all the attendees to consult or download our strategic plan from our website. So our strategic plan gives special importance to education. We are currently, as you know, probably funding several education programs, including Distinguished Lectures Program, Virtual Distinguished Lectures Program, Industry Distinguished Lectures Program. I'm happy that our friend Massimo is here with us. In addition to that, we have seasonal schools, and this is one of them. This is one of the seasonal schools we are funding. We have micro-learning program also, and e-books program. And we intend to put in place a better coordination between all these programs by creating a CASSW Global Education Institute, which currently exists in the form of an ad hoc committee created this year and chaired by Professor Franco Maluberti. We are thinking on going beyond coordination by providing support for the creation of new curricula, by endorsing university training courses, etc. So this is a strategy. I think this is something we are going to work on it the beginning of next year. So our resource center will be the backbone of this institute, as all our education programs are generating outstanding contents that will feed our research center. That's why we are planning to redesign completely our resource center based on a new architecture and a chatbot to make the navigation and the search easier. So I don't want to take too much time. I am really very happy to at least participate to the opening of the school, and to conclude, I wish to your seasonal school, to your workshop, very big success, and see you in other occasions. Thank you.
Thank you for thank you for your kind words, Amara. CAS plays a huge role in our day-to-day operation here. We couldn't do anything without your actions in the top level. I would also like to thank Ricardo for being here. He's also one of our program chairs. So Ricardo will give us a few words on Region 9 and also on the program. And right after Ricardo, Fabio will also say a few things about the poster session. So how it will work, days, and so on. So thank you, Ricardo, and thank you, Fabio, for being here.
Thank you very much. So thank you all you that are here to join this 10th edition of the CASSW Rio Grande do Sul workshop. So in reality, I'm not going to talk too much about Region 9 now because we have a session this afternoon dedicated to present the activities and the report of the CASSW Rio Grande do Sul chapter and also the Region 9 activities, and so join us this afternoon. So I'm just going to give a brief overview of the program. So thank you all the invited speakers that accept our invitation. Thanks to all that submit a poster to this event. Then Fabio will talk a little bit later. So the program starts today with just after this opening session, we have Massimo Alioto that will talk about circuits and architecture with ultra-wide power adaptation for next generation always-on systems. So he's from the National University of Singapore, and Professor Sérgio Bumpi will be the session chair. After a short break, we are going to have the second talk of this first morning here in Brazil, and the talk will be done by Erik and Marinissen from IMEC, Belgium, talking about 3D test and design for test challenge and solutions. And the session chair will be Professor Thiago Balin, that is the head of our graduate program of microelectronics here at Federal University of Rio Grande do Sul. Then this afternoon, we have a talk by José Gabriel Gomes. I'm not going to read all the details of the talk because you have in the program. And the chair will be Professor Bruno Zatti from Federal University of Pelotas. And then we have 3 p.m. Brasilia time, that means GMT -3, talk about opportunities within security system society that will be presented by José Zambuja, talking about the activities and actions that is being done by the Rio Grande do Sul chapter. And I'm going to talk a little bit about Region 9 activities. And then we have a short coffee break and then the first poster session. Then tomorrow morning, the talk will be generated in Bordeaux, France. So Yann Deval will give the talk, and the chair will be Professor Paolo Recchi. Then the second talk tomorrow in the first session is with Krishnendu Chakrabarti from Duke University. The session chair will be Ricardo Jacobi. As you should know, Chris is also the chair of the CASSW Distinguished Lecture Program. Then in the afternoon, we have Marcelo de Souza from Federal University of Paraná. And the session chair will be François Rivet from Bordeaux. Then another short coffee break, and then the second poster session. Then Thursday morning, we start with Matteo Reorda from Politecnico de Torino, and the session chair will be José Zambuja, that is our chair of our chapter. And after that, we have a talk by Srinivas Katkori from University of South Florida, and the session chair will be Luciano Osto from Loughborough University in UK. Then in the afternoon, we are going to have a talk by Lawrence Clark and from Arizona State University. So talking about the PDK they do there. And the session chair will be Christina Meinhardt from Federal University of Santa Catarina. Then another short coffee break, and then the third and last poster session. Then Friday morning, we have Pascal Vivet from CA Leti in France. And the session chair will be Professor Fernando Moraes. And then we have Aida Trodi Sanial from LIRM Montpellier, and the session chair will be Omar Paraíba from Minas Gerais. And then in the afternoon, we have the specific session of the second Young Professionals workshop. So all the posters is also in the context of the Young Professionals workshop also. And this session will be in Portuguese, and Professor Marcelo Lubaszewski will be the chair, and he, together with Camila Vargas and Sérgio Finger, will talk about the future of the work, technology, education, and the market. And so then we have, after a short coffee break, the closing session and award ceremony. So as you know, the posters, the best posters, we receive a nice award, and then we close with a social event. Then, so here details about the, and then next week we restart the last 2 weeks of our industrial talks of this season. So this is the first season of the series of industrial talks, and the talk will be done by Daniel Henrique Musquiano from Alego, Argentina, talking about 20 years of IC design in Argentina by Allegro. And then on Friday, we have a talk by Dr. Maria Mustak from LIRM Montpellier, talking about microarchitectural vulnerability assessment and mitigations. Then Wednesday afternoon, the last industrial talk of this year, this season, João Batista Martins will talk about the work of Santa Maria Design House and the development of ASICs and radiation-hardened integrated circuits. And then to finish also the season on the CASSW talks, we have a Professor Jan Rabey from UC Berkeley that will talk about off-brains and computers. And soon you are going to have also his abstract. So this will close the 8th edition of our CASSW talks, 8th season, and the first virtual season, let's say. So you are going to have more details about all this process in an article that is going to be presented in that's going to be in the next edition of CASSW magazine that should be launched next week. And then in December, we have 2 very interesting seasonal schools, Cereza 2020, that will be the celebration of 15 years. So the 16th International School on the effects of radiation on embedded system for space application, that this year also has CASSW as one of the technical supporters. And so the first one was in Brazil, in Manaus, 15 years ago. Then it went to Seville, Buenos Aires, Palm Beach, Takasaki, São José dos Campos, Toulouse, Amsterdam in South Korea, Moscow, Bariloche, Puebla, Montreal, Munich, Nordwijk, Seville, and now a virtual edition from Porto Alegre with 23 speakers. You can go to the website to see the full program, and also the call for posters is still open till November 20. So please, if you work in these topics, go to the web page to see more details about the poster submission. Then we have another seasonal school in the week after on electronic design automation. So this is in the series of CASSW seasonal schools. So it's going to be generated from Santa Catarina. If you address the web page now, you can still submit your poster for the poster session with very nice awards for the best posters. And the registration is open, and the registration is free. Like in Cereza, the registration is free for all CASSW members. The other ones have to pay a very small registration fee, but so the registration for this seasonal school electronic design automation is already open. Then 16 and 17 December, we have our local CASSW meeting. So this is going to be in Portuguese. and on December 16, we are going to have a large set of videos done by former students from here that now are working abroad. So I think you are going to be surprised with the large and nice set of people that will be giving their few words and so on. Well, I'm not going to talk about the whole program. And then December 17 is dedicated more to our reports and planning for next year and so on. And so now I give the floor to Fabio to talk a little bit about the author sessions.
Good morning, everyone. I think everyone is listening to me. I'll try to give a brief overview, also because I have a toddler running wild around here in my house. So we have 34 posters accepted, which will be presented in 3 days, starting by today, Tuesday at 3:45 p.m. And on Wednesday and Thursday, it will start at 3:15 p.m. We encourage the audience to address questions during the poster sessions in the YouTube chat. We will compile them to be later answered by the authors. And after the poster sessions on each of these days, there will be a synchronous activity with the authors, which we will address the questions that we collected on the YouTube chat, and also any possible on-the-fly question that the audience have during the synchronous activity with the authors. And that's it. That's my brief overview. I appreciate to be here with you, all of you today.
Thank you all for your information. To finish the opening panel, I would like to thank all our viewers. Wish you all a great event, and thank our organization for making it possible. So I will now be adding Massimo and Bumpy, who are going to be our first talk today, and removing our panel here. So thank you again. Thank you, Amara. Thank you, Ricardo. Thank you, Fabio. And thank you, Thiago, for participating. And let me just add here Bumpy and Massimo while I...
Thank you.
Well, thank you all for being present here at this opening session. The CASSW chapter in Rio Grande do Sul is very honored to present the first talk this morning or day of the 10th edition of the school. We'll have 11 talks in those 4 days, as already mentioned previously. And the first talk will be given by Massimo Alioto. Let me introduce Massimo, the speaker this morning. Massimo will speak about ultra-wide power adaptation for next generation always-on system. And Massimo is out in Singapore now, where he is a professor at the Electrical and Computer Engineering Department at National University of Singapore. He's the leader. Excuse me. He's the leader of the Green IC group, the Integrated and Embedded System area, and the FD Fabrics Industry Sponsor Lab on FDSOI Intelligent Interconnected Systems. He has been previously associated with several institutions. He worked at the University of Siena, Intel Labs Circuit Research, University of Michigan Ann Arbor for a few years, and University of California, Berkeley, and EPFL. He is a very prolific author of 300 plus publications on journals and conferences. He has published 4 books, including the one that calls that's titled Enabling the Internet of Things for Integrated Circuits, Integrated Systems. As you all know, Massimo's primary research interests include ultra-low power circuits and systems, self-powered integrated systems, near-threshold circuits for green computing, and what we're going to be speaking today, widely energy scalable integrated systems, circuits for machine learning, intelligence, hardware security, and other applications. He is currently editor-chief of the IEEE Transactional VLSI Systems. He was a deputy editor and have several editorial board assignments. He served as a guest editor of several issues, and his technical program of many members. So it's our pleasure to have Massimo. Massimo is also an IEEE fellow, should add, and he will be speaking for this hour on this very exciting power adaptation issue for next generation always on system. So the floor is yours now for the first talk of the workshop, dear Massimo, and please say hello and certainly our audience will appreciate very much what you have to share with us this day.
I guess you can hear me okay?
Yes, you are being heard.
Good. Well, first of all, thank you, Sergio, and thank you all. I'm very honored to be to introduce this talk, the first talk to this event, and I'm really amazed by the energy that is behind the organization of this event. In spite of this quite unique, quite peculiar situation worldwide, it's really encouraging to see that there is a lot of vibrancy and energy. And by the way, I would love to be in Brazil right now, but unfortunately, that's not an option. Now, let us move on and let us plan the next hour, the hour that we'll spend together. We're going to talk about one of our research areas that we are investigating, and this is about ultra-wide power adaptation to enable next generation always-on systems. So this presentation is structured as follows. First, we'll talk about the context and the motivation. So we'll share that actually things are a little more complicated than we usually tend to think. So adaptation is an essential property and requirement in always-on systems. Then we'll talk about how to scale up performance, reduce power down to the very minimum that complies with the very limited power budgets offered by energy harvesters, and then I will wrap up. So let's get started with energy autonomous integrated systems and what they really are. Well, essentially, we're talking about IoT nodes. So the nodes, the devices that are at the lower tier, and let me just actually enable the pen so that once in a while I'll be able to highlight things for you. We are focusing in this presentation on at the edge of the IoT. So sensor nodes with very limited power budget. And by the way, sensor nodes were expected a long time ago to be mostly dormant and being duty cycled. But these days, actually, you want them to be very responsive and always on or mostly on. And this poses a very fundamental challenge in terms of power consumption and its trade-off with performance, which is the core of this presentation. Now, everything is really constrained by the energy and power availability in IoT nodes as available from the source, the energy source, which is typically a hierarchy. You might have an energy harvester, a battery, and hopefully miniaturized, as well as a supercapacitor. And those are combined in proper ways to achieve the best of the two worlds. For example, the high energy density of energy harvesters and the high power density of supercapacitors and or batteries. Now, depending on what type of energy source we have, the average power certainly matters, and it is the main concern in battery-powered systems, because this essentially determines the lifetime of the system. So you will have a decay in the energy stored in the battery. Once it hits zero, the system stops working. And the slope is basically dictated by the average power of the system. Then you can have hybrid energy sources. So you're going to complement the battery with, let's say, an energy harvester, let's say a solar cell. And in that case, essentially, you are reducing the power, the amount of power being withdrawn by the system by the amount of power that is being provided by the energy harvester. And if the energy, the power of the energy harvester actually completely offsets the average power absorbed by the system, then you can actually aspire to nearly perpetual operation. So we're talking about decades of operation for typical integrated systems. Then you have a third and increasingly important category based on pure harvesting. So there is no energy storage. There is only harvesting. And this means that the peak power, whenever the peak power goes beyond the available instantaneous power from the harvester, the system gets shut down. So again, the lifetime will be limited, not in its extension, but in terms of intermittency. And then you have a new class, a recently proposed class of systems that is called battery indifferent, where you can operate off of a battery to continue operation at higher performance whenever the energy in the battery is available. Or if the battery is empty, is running out of energy, then the system can still operate continuously by tapping into the power availability from the energy harvester. Of course, at limited performance. But this allows to combine these two to extend the availability of the system in spite of the intermittently available energy in the battery. Now, we all know that classically, what we do to reduce the average power is to sleep most of the time and have once in a while some active task. And more duty cycle, more aggressive duty cycling, it means longer sleep for a given active mode, means lower average power. But actually, and this is actually pretty easy to achieve, but this comes at a price. The system will be mostly dormant, mostly unavailable. And the power can also be further reduced through voltage scaling. Now, in recent systems where it's actually, the main purpose is to detect events and then turn on data analytics, on-chip data analytics, whenever there is an event of interest, well, those have to be always on, and it means that their level of performance need to be very different depending on whether an event is occurring or not. For example, if you have a speech recognition system, if there is no speech, as we have here on the left, well, then you don't need to actually turn on the speech recognition system because there is no speech, and you have a speech detection system. When there is speech, then you turn on the big machine learning engine, and this will come at a power cost, but occasionally, and it will require a much higher level of performance. So this is really what the IoT is requiring more recently, which is you need to achieve low energy in the common case to make sure that the average power is low and complies with the lifetime target of the system. But at the same time, the maximum performance, although occasionally it matters as well, because sufficient performance has to be delivered whenever there is an event of interest. So, and in this case, you want to scale up the voltage and even boost up the performance in any possible way, which is what we are going to discuss in the next few slides. By the way, there is another concern that we need to take care of. So, for example, in battery indifferent systems or in purely harvested systems, the power of the system need to comply with the power availability from the harvester, and this is instantaneous. So if, let's say, you have a solar cell that is actually providing very little power because the lighting conditions are being not very favorable. Let's say you are indoor and it's, let's say, twilight. Well, in that case, you have little power, and the system has to reduce this power down to what is called minimum power. So in this case, it's not about energy, it's about power. Okay? Now let us try to make sense of what type of power we are talking about. Well, if you look at practical harvesters, they typically, and I'm referring to a few references. By the way, at the bottom of each slide, you will see a few references that you might be interested in exploring further later on, and I will be more than happy to share the slides with any of you so that you can dig more after this presentation. Well, if you look at commercial harvesters, typically they deliver in optimal conditions tens of nanowatts and maybe a few hundreds of nanowatts per square millimeter or cubic millimeter, and even down to nanowatts in unfavorable conditions. Now, let us assume that we have this power budget because we want to keep the harvester in the millimeter scale. So we want the system, the IoT systems the system to be unobtrusive, so millimeter scale. Well, in that case, let's assume we have a very simple microcontroller unit, let's say an ARM Cortex M0, and let's say a typical configuration, 100 kilogates. Well, if you divide nanowatts or tens of nanowatts by 100 kilogates, this results into deep sub-picowatt per gate. Well, as you understand, the typical leakage, even in high VT flavors of low leakage technologies, this is at least several nanowatts, at least. This means that we need to actually reduce the power consumption compared to pure leakage by essentially 2 orders of magnitude. Well, this means, and that's very interesting, that's the first finding that you should really retain in this presentation. You actually need, if you want to comply with the power budget offered by practical harvesters, you need to run at a power that is even below leakage. That seems hard to do. Well, it's not easy, but it actually can be done, as I will show in the next few slides. So overall, we don't have really a single target for event-driven and most recent IoT devices, and certainly next generation IoT devices. You actually have 3 targets. The first is minimum energy, so that the corresponding power, whenever you perform a certain operation regularly, will be minimized. Then you want to scale up to maximum performance, second target, whenever an event occurs. And in that case, you need much more performance than in the common case. And then third, we need to pursue minimum power whenever a power event is occurring, which means that the power from the energy harvester, assuming that the battery is now discharged, this is the power event I was referring to. Now you have to comply with the very tiny power budget of the harvester, which means you need to really reduce power as much as possible. So 3 targets, not 1. Well, the first one, minimum energy, has been explored in all possible ways in the last 15 years. And I will say very little about this. So basically, you want to optimize the voltage around the minimum energy point, which is well known to exist in any technology, and it depends on the specific architecture of the system. This has been explored extensively, so I will not say much. So voltage scaling certainly helps. And you also want to reduce the design margin of process voltage and temperature variations at design time. And here I'm just pointing out at a few publications we have published to mitigate and solve the problem, or to have even a margin, process voltage temperature margin elimination by measuring the actual minimum clock cycle through timing sensors. Let's move on, which is what lies ahead. So this has been done extensively. So how do you scale to maximum performance occasionally without compromising the minimum energy operation? So without compromising the first target? Well, before doing that, let me just observe that typically you're going to operate in any, let us start with simple with a digital circuit, and then we'll expand to sensor interfaces and power management. Well, typically transistors are going to operate in 3 wide ranges of voltages, which are strong inversion, about threshold operation, moderate inversion, which is near threshold operation, and weak inversion, sub-threshold operation. And if you look at a few designs that have been proposed over time, you can see that the performance degradation at the minimum energy point compared to the maximum performance, which means nominal voltage, is in the order of several tens of x, okay, and up to 2 orders of magnitude. Whereas the energy improvement at the minimum energy point compared to the nominal voltage tends to be an order of magnitude or sometimes lower, okay? So the performance degradation is heavier than the energy benefit that you get out of it. Now, the reason why actually it's not very easy to pursue at the same time maximum performance and minimum energy operation is twofold, actually. The first is, if you look at the clock path of a digital IP, it might be multiply and accumulate array or a microprocessor, is that the clock network actually is optimized at a given voltage in all practical designs and in all commercial designs, by the way. But actually, the number of clock repeaters heavily depend, the optimal one that will minimize the clock skew and will optimize the clock skew versus energy trade-off heavily depends on the voltage. So the question is, should I actually design optimally the clock network at nominal voltage so that I will have maximum performance, but then I will degrade energy efficiency and even reliability at lower voltage, or vice versa? So we have to make a choice traditionally. And same applies to the microarchitecture. So should I use a large logic depth or a lower logic depth? Because this actually changes completely the leakage versus dynamic energy trade-off. And this, in turn, translates into a different energy performance trade-off. And again, if you set this properties and you make these choices at design time, you're not going to be able to pursue at the same time maximum performance trade-offs, maximum performance trade-off and target whenever performance is needed, or minimum energy trade-off or target whenever, in the common case. So at design time, if you don't have enough flexibility, you need to choose to privilege, to favor performance or energy. You can't have both at different times with the same circuit. So what is the solution? And on this, I'm really referring to a book that we have published a couple of months ago on adaptation for digital circuits. So you can dig more and have a look at this book to know more about this. Here, I will give you really an overview of the challenges that we have recently solved and the challenges that lie ahead. So overall, what you want to have is reconfiguration, both in the clock path and in the data path. This is what we are going to talk about in the next 10 minutes. Let's get started with clock networks, okay? And we want to introduce reconfiguration. In a traditional clock network, and I'm referring to the blue curve, if you are designing at nominal voltage, there's nothing you can do. This will certainly lead to a deep clock network, like the one on the top here on the right of the slide. You will have several levels of clock repeaters because you have to minimize the wire delay so that you can run at high speed. So you are going to interrupt the wire delay, the wires, as often as necessary to minimize the clock skew and maximize the performance. And if you reduce the voltage, you can see that the clock skew increases simply because at low voltage, so I'm referring to this end of the curve, at low voltage, actually, the wire delay remains the same. The clock repeater delay becomes much higher. So now you don't need to actually insert as many repeaters. So you will prefer to have what is called a shallow clock network. But the thing is that at design time, you have to choose whether to have a deep or a shallow clock network. So if you choose a shallow clock network, what happens is that here, you're going to have a low clock skew at low voltage, but then the clock skew at high voltages, so nominal voltage will be much higher. So it means that now the performance will be impacted very heavily, will be degraded. So what you can do is to go beyond traditional design frameworks and introduce the concept of reconfigurable clock networks. The only actual difference between a fixed conventional clock network and a reconfigurable clock network is the presence of this bypassable clock repeaters. So this can operate in two different modes. The first is, let's say, at nominal voltage, you want all of them to function as clock repeaters. So they are not bypassable. They are not bypassed. They operate in normal mode like any other conventional clock repeater. So you can pursue high speed. Instead, at low voltage, you want to eliminate most of them. You want to bypass most of them. And this is done by selecting the bypass mode in those clock repeaters, where you have basically a switch that bypasses and merges the neighboring wires to have longer wires and a different subdivision of the clock network between between different levels. And this can be done, for example, this is just a possible implementation. This can be done in many other ways. This is the topology of a bypassable clock repeater. In normal mode, this is off, and this works like a normal repeater. In bypass mode, instead, this will be turned off through sleep transistors, and then you have a pass transistor that is just that connects the input and the output. Well, that means that this no longer operates as a logic gate. It operates like a short circuit, basically. The good thing about this simple approach is that you will actually need to bypass clock repeaters only at very low voltage, right? And this means that if you just apply nominal voltage, which is invariably available in any design, to the gate of these transistors, these pass transistors actually will be inherently much stronger than all other transistors. So it means that you can actually keep them pretty small. You don't need to upsize them significantly. And this explains why in, for example, in a 256-point FFT design that we have demonstrated, and then we'll talk about that in the next few slides, the area overhead of this approach is very limited, and it's less than 2%. So how to make this work? Essentially, you want, based on the voltage, you want to have a certain number of bypassed repeaters. No bypass at the highest clock frequency, all bypassed at the lowest frequency, right? And anything in between for intermediate voltages, okay? So apart from the traditional table that associates voltage and frequency for dynamic voltage frequency scaling, you need to augment this table with the indication of which clock repeaters need to be bypassed and which should not, okay? So from an implementation point of view, actually, it's pretty easy to have reconfigurable clock networks. You just need to augment the traditional DBFS table with the third column that specifies what the configuration of the clock repeaters should be at every voltage. Now, once you optimize, you choose the optimal clock skew optimal configuration of the clock repeaters, you're going to have these blue curves in terms of clock skew versus voltage. As you can see, the clock skew in terms of FO4 delays, where FO4 is the well-known delay of a single inverter gate driving 4 equal inverters, remains a very small fraction of FO4, as it should be, okay? So you don't see the explosion of the skew at low voltages. And to be more precise, if you actually adopt a fixed clock network, this is what you get. At low voltages, you get an increase in the clock skew by more than 3 times. And this is very harmful in terms of both reliability, robustness, because now hold time violations in registers is much more likely, as well as performance, because now the fraction of the clock cycle eaten by the clock skew is increasing, which means that now the performance is degraded. Instead, if you adopt the optimal configuration, you're going to reduce the skew and you are going to keep it basically nearly constant or so, okay? You're going to mitigate this very substantially. What is the effect of this? Well, let me just comment on the 2 aspects that I mentioned before. One is hold time violations? Well, if we actually manage to reduce hold time violations, thanks to reconfiguration, what happens? Now you can actually operate at lower voltage because the clock skew is reduced. And that's exactly what happens. You can reduce the operating voltage, the minimum operating voltage, by more than 100 millivolts. Now your sensor node can actually have wider voltage scaling. And this also improves the yield because the hold margin is increased. At the same time, of course, you get an increase in performance, as you can see here, 8%. That's not very significant because when you operate at, let's say, 0.4 volts, a minimal increase in supply voltage will actually get you 8% of performance increase. So that's not really a real advantage. What is an advantage is that now you can actually reduce the operating voltage. It means that you can benefit from the further quadratic energy benefit offered by voltage scaling. And that's why you're going to get an 1.4x, so 40% energy reduction compared to the original fixed design. Okay? And this explains why clock network reconfiguration allows to improve the trade-off between performance, reliability, and energy. It basically relaxes this trade-off. It allows to improve all of them whenever you're pursuing higher performance, lower energy, and higher yield and higher reliability. Now let us look at the data path. We have talked about the clock path. Let us talk about the data path. Well, essentially, the question is, should you adopt a higher logic depth, so few registers with very long pipe stages with a lot of cascaded logic gates, combinational logic gates, or you want to go the opposite, so a lot of registers with very little combinational logic between neighboring registers? Well, as usual, there is an optimal logic depth that determines the minimum energy point. And this minimum energy point actually depends on the architecture. And by the way, you might want to actually adapt this minimum energy point depending on the performance level that you're pursuing. Let me be more specific. And let us consider the case where you just set VDD. Okay, you set VDD and you want to choose the logic depth. As it's easy to imagine, shallow pipelines, it means few registers and long combinational logic paths are preferable because you have fewer registers, right? So at a given voltage, the deep pipelines with more registers have higher energy, right? At low voltage, it's the opposite, because deep pipeline has actually lower energy simply because you have shorter pipeline stages, so shorter delays in the combinational logic, which means that you integrate leakage, so the leakage per cycle becomes smaller because the clock cycle is smaller, right? So again, if you choose the logic depth at design time, you have to choose whether you have high energy efficiency at higher voltages or lower voltages. Instead, if you have adaptation, you can adapt to both and get the best energy efficiency in both cases. And if you look at the comparison of different microarchitectures at the same throughput, then similar configurations considerations hold. They are actually inverted, but you basically come out with the same conclusion. If you choose a design time in a fixed, rigid manner, you're not going to be able to pursue energy efficiency at all voltages. You will achieve it in certain ranges and not others. So the question is, how do you reconfigure microarchitectures? The answer is pretty easy, and you can look at a paper that we published 2 years ago in JSSE. Essentially, you have bypassable registers. Normally, you don't bypass, so you have a multiplexer at the output where you don't multiplex the flip-flop. So basically, the flip-flop keeps operating like a normal flip-flop. Instead, if you want to bypass it, you're going to select the other input of the multiplexer so that the input of the flip-flop goes directly to the output. So basically, the clock is irrelevant. You're not really latching the information, okay? And then if you bypass, you're essentially merging. If you bypass this, you're going to merge this into a single pipeline stage, right? So you're now virtually expanding the logic depth of this pipe stage. Now, how do you choose this and how do you actually enhance traditional voltage scaling, voltage frequency scaling with the ability to merge pipe stages and adaptively change the logic depth of pipe stages? Well, the answer is the same as before. Apart from the traditional table with voltage and frequency, you add the configuration of the registers, choosing whether you need to bypass or not. And you will choose the configuration that maximizes the energy efficiency, okay? Based on the criteria that we mentioned before. So again, the implementation is actually quite easy. You just need to enhance the DVFS table with this third column. And if you want to do all of them, so data path and clock path being reconfigurable, you will have a third column with clock reconfiguration and a fourth column, which is data path reconfiguration. Let me just share with you what happens with an example, which is pretty representative of practical applications. You have a 256.16-bit radix 4 fixed point complex FFT, which has hundreds of kilogates. So that's representative of typical design IPs for IoT, not very big, not very small. And what you can see is that you can have at about threshold voltages, you can reduce the energy by 25%. So this is what we are referring to. And at lower voltages, you can do pretty much the same. You can reduce energy by 30%. So what we are seeing is that the optimal selection of the microarchitecture, so the data path configuration, allows you to reduce energy both at higher voltages and lower voltages, depending on whether you want to have more performance or lower energy and power in the common case. So you don't need to choose at design time. At runtime, depending on what performance trade-off you're pursuing or what performance target you're pursuing, you can adapt and reduce the energy in either case. And the throughput is degraded by the presence of multiplexers and reconfigurable registers by less than 6% at the maximum maximum performance target, with the area increased by 3%, which is quite okay with for all practical purposes. I will skip this and I will focus on design methodologies. This is actually a talk by itself, so I will probably skip through. But I would like to mention that we have also developed a complete design methodology and a design flow for reconfigurable microarchitectures and logic depth, as I mentioned before. And this can be applied to any practical design. It's available on GitHub. You can just download it and use it. So you can just use this QR code and download the set of scripts that we have created to enable this capability in design and architecture agnostic fashion. Let me just share with you that the materials that we have put on GitHub allow to first do a pre-designed path analysis to foresee what the benefits will be after the design, but you can actually foresee this before doing the actual design. And second, these scripts and the overall design flow actually operates on gate level netlists. So this means that even if you have, let's say, an ARM core or any third-party design IP that is being synthesized, and it's obfuscated because it's protected, because it's third party, you can still adopt this methodology without any limitation. So you can apply our methodology to your designs or third-party designs. And you can refer to these two publications if you want to know more about this design flows. One is TVLSI, a paper that we published a couple of months ago, and one is the book that I mentioned at the beginning of this presentation. Now, this only solves 2 of the 3 design targets. There is a third one, which is minimum power operation whenever the battery is no longer available because it's depleted. And this is actually a very realistic scenario and very frequent scenario whenever you miniaturize the system to millimeter scale batteries. Such small batteries will get depleted very often. And in that case, you need to survive and keep sensing and processing even when you have only power from the energy harvester. How to do this? Well, to follow through the thread that we have gone through so far, I will start from MCUs, so digital subsystems, and then I will enrich with power management and sensor interfaces. Well, basically what you want to do is to extend the power dynamic range offered by voltage scaling. You can actually extend it down to nanowatts as required by energy harvesters by using other logic styles, for example, dynamic leakage suppression logic style proposed by University of Michigan, as well as Q11 a few years ago. But this doesn't allow you to actually have a complete and flexible trade-off. So what you want to have is to bridge the gap between the existing standard CMOS logic style and other more sophisticated logic styles that reduce power. So you really want to fill this gap and have a continuous power performance trade-off. This can be done by using an approach that really achieves both the properties of CMOS logic whenever minimum energy or higher performance is needed. So this is standard CMOS logic. And you want to also reconfigure your system and your circuit to mimic DLS, dynamic leakage suppression logic that I mentioned in the previous slide, whenever minimum power is being pursued. How to do that? Well, as you understand, architectural reconfiguration is not enough. You really need to go down to the circuit level. So you need to introduce what we call dual mode logic, which is at the right of this slide. And I will talk about this in the next 2 minutes. You can find more details in a paper that we published at ISSCC 2 years ago and other journals that came after. So the main principle of dual mode logic is that if you actually turn on these 2 transistors, 1 and 2, in each standard cell by just raising the gate voltage of this NMOS transistor, the upper transistor, beyond VDD, and the PMOS transistor below ground, and this can be done with very low power charge pumps, very low power because they are just driving a capacitive load. There is no DC current being absorbed by these transistors, right? So in this case, this will go to VDD and this will go to ground. Well, then this transistor, these 2 transistors are just an inverter gate. So this resembles conventional CMOS logic. Okay, so this circuit is able to mimic standard CMOS logic. At the same time, if you instead turn off these 2 transistors in green, now the rest of the circuit in the standard cell mimics, is actually completely equivalent to DLS logic, which is femtowatt per gate type of power, deep subleakage as needed. So you have reconfiguration based on whether you turn on those two transistors or you turn them off. And this is what you get. Dual mode logic is able to, on one hand, achieve minimum power that is almost best in class compared to others. This is nanowatt level, even sub-nanowatt level for practical MCUs. But at the same time, they can achieve a performance that is comparable to most or superior to most existing MCUs. So this is MCU, 16-bit. This is MSP430, like MCU. And as you can see, it has the ability to go down to nanowatt, while still, so it means that it's suitable for continued operation based on millimeter scale harvesters, and it has 6 orders of magnitude power performance trade-off. And by the way, this tells you really what each of those techniques enables. So voltage scaling allows 2 to 3 orders of magnitude power performance scaling. Then if you apply data path or microarchitectural reconfiguration, you go up. You extend the dynamic range by another order of magnitude, so this one. Then if you want to extend by another 2 orders of magnitude, you really need to go for dual mode logic. And that's quite expectable. Basically, in the first category, this one, voltage scaling enables power performance scaling. Then if you want to further enhance it, you're going to go for architectural scaling. And then if you want to further enhance it, you want to go for circuit reconfiguration, right? And you reach 6 order of magnitude scaling. Now, let me clarify that this is just an example, and this can be applied immediately to sensor interfaces. And this is just an example. So the main challenge whenever you have a complete system where you have power management, sensor interfaces, as well as digital subsystem, what you want to do is to remove the power floor, which means the minimum power of any existing subsystem, so that all of them will keep scaling if you need to, at the cost of lower performance, of course, but you don't want to have a power floor imposed by any of those, let's say, leakage for digital or bias currents for analog. You actually want all of them to keep scaling down if you need, and if the battery runs out of energy. And this has been done in our group. It has been demonstrated in the last 2 years. And we have shown that sensor interfaces, especially mostly digital sensor interfaces, instead of being just digital assisted, you really want to move to mostly digital so that you can get the similar benefits as the digital subsystem. And both of them, both the analog and the digital subsystem, are able to scale down in terms of both power and frequency in a coordinated manner. So if you scale down the power on one of these two, the other one will adapt equally. And same in terms of performance. So none of those will be the performance or power bottleneck. They will scale together. And this is an example. I will not go through the details, but I will encourage you to go through the JSSC publication of a few months ago. Basically, we presented a multi-sensor interface that is able to coordinately scale with a microcontroller unit and go down to nanowatts and up to a few mega sample per second sample frequency. Well, this tells you that for IoT, whenever you have power, you can actually cover most of the applications. So you can go up to mega sample per second. But if you don't have power because the energy in the battery is really running out and you need to comply with the power budget of an energy harvester, then you can run down to 3.1 nanowatts, all included. This includes digital, power management, as well as sensor interface. So again, you have 5 to 6 orders of magnitude power performance trade-off, including sensor interfaces. How useful is this? because this is, of course, more aggressive than architectural reconfiguration? Well, this actually enables an unprecedented scaling in terms of power and compliance with the power budgets coming from harvesters, even in under very unfavorable conditions. Let's say you are operating with a 4x4 commercial harvester, solar cell. So in indoor light, this is what you're going to get, okay? You can go down to this, and this is what voltage scaling allows you to do. If you want to keep operating under indoor light, and this is the typical indoor light, our approach allows to do that. So even with no battery, the system keeps going. Now, let's assume you're operating in a home environment with very dark light in an overcast day. So we're talking about tens of luxes, okay? The system keeps operating because the power is still in the order of hundreds of nanowatts from the harvester. Now, let's assume it's going pretty dark, 10 lux, okay? And now let's be even more extreme. Let us go to 1 lux. Well, you know what 1 lux is? 1 lux is moonlight. So yes, and if you actually look into this QR code, this will lead you to a demo, live demo, that you can actually watch with your smartphone. Essentially, the system is able to run down to moonlight. It means that it's unstoppable. It can be always on, even if there is no energy in the battery, and even if the harvester conditions are very unfavorable. So on all practical respects and under any practical lighting condition, our system proves to be always, truly always on. And there is a lot of work going on to further reduce this the power cost of the different subsystems. So here you will find a summary of publications that we have in this area. And I would like to summarize beyond this. So we have covered amplifiers and ADCs and DACs and voltage references, oscillators, and so on and so forth. So all practical peripherals that you find in an IoT system. But beyond that, I would like to summarize and give you the the fundamental message of this presentation. Next generation IoT systems are not going to be single target. They actually are going to be multi-target and event-driven. Why? Because first, you want them to be minimum energy per operation whenever they are operating under battery energy. Whenever there is no energy in the battery, or actually, sorry, before that, whenever there is an event of interest, signal event, you want to respond and increase the performance to perform data analytics on chip. So this means maximum performance. So you need to scale up performance. How to do that? Architecturally and through conventional voltage scaling together. This buys you another order of magnitude of power performance trade-off. Then, if the battery is running out of energy, you want to keep running, and this means that whenever there is a power outage, a power event, you want the system to keep sensing, processing, and storing into the memory at nanowatt level, so minimum power operation. And then a fourth capability that will be required is, let's say there is really no harvesting power at all, or so even lower than moonlight, so something that is really catastrophic. You still want to retain at least the basic events that were being stored in the memory. In that case, you want to at least keep the system functioning correctly and retaining the basic functions and the basic information stored, even if there is really not much power from the harvester. And then let's wrap up. Well, I guess we all remember what this is. Probably keeps us in a good mood. Let us wrap up. Let us see what we should retain from this talk. First, next generation IoT devices are not going to be single target. They are going to be 3 targets: minimum energy, to have low power in the common case when they are battery powered and always on. Second, maximum performance. So you want to boost up the performance by at least an order of magnitude whenever, or even more, whenever you need to perform data analytics of events of interest. And then if there is a power event, so no battery, you want to respond by reducing the power to the level that is available from the harvester. And this requires a very wide and uncommonly wide power performance trade-off. And this is accomplished through traditional voltage scaling. It only gives you so much, right? Then you have to augment this through architectural reconfiguration, and you buy another order of magnitude. And then you can have circuit reconfiguration, which buys you from another 1 to other 2 orders of magnitude. Well, these capabilities, other than keeping our systems on and mostly available all or most of the time, allow us to shrink batteries by 1 or 2 orders of magnitude, which actually is a good thing to do, not only because of the cost and the implications in terms of form factor. So shrinking batteries or eliminating batteries is a good thing to do on those respects, so form factor and cost. But eventually, considering that we are going to deploy otherwise 1 trillion batteries in this planet, and this is going to create an unprecedented level of pollution, well, the removal of batteries, or at least shrinking batteries by 1 to 2 orders of magnitude, will make our planet a little greener, which I think is a mission that we really need to think about when we do research. You know, our planet cannot really take another extra 1 trillion batteries. Well, before I say, I will leave the floor for further for questions, I would like to really thank my group and my students and researchers. It's just it would be just impossible to do what we are doing without their contribution. So what I do is I share with you what we are doing, but the real work is really being done by our students at the Green IC group in Singapore. And then if you're interested in digging more in scientific contributions that provide some new directions, you can look into a few special issues that we have been leading. This is TCAS1 and JetCAS 2 years ago. One book that actually, this is the one that I presented at the beginning of this talk. This is a Springer book on adaptation of digital circuits, and another book on IoT. This is actually the first book on IC design for IoT that was presented a little more than 2 years ago. And an upcoming book, if you're interested in how to get rid of 1 trillion batteries and make our planet a little greener, well, that's coming up in a couple of months. But I cannot really tell you the title, so it's all top secret right now. So just stay tuned. And if you're interested in attending our MID courses, this is the first actually in Asia on energy-constrained integrated systems. Just stay tuned and feel free to contact me if you want to have more information. We had the first edition, and during the COVID year, we didn't have it, and we are going to have the 2021 edition in a couple of months. So thank you very much for your attention. I will be more than happy to answer your questions. Thank you.
Okay, thank you, Massimo, for this very interesting talk. We have many questions here coming in the channel from the audience. The first one has to do with asynchronous, okay? Marco Sartori, a PhD student here in Porto Alegre, and also David Harvey from Liverpool are asking those two questions regarding the clocking strategy. Why not get rid of the clock networks altogether? I understand going asynchronous. And from Liverpool, why not go for asynchronous clocks? No clock delay is an issue, only edges and level changes. So there are questions related to timing disciplines that they are considering as alternative for ultra low energy.
Well, first of all, I would like to thank for the very good question. And conceptually, both attendees are totally right. Conceptually, it would make sense to get rid of clocks. In practice, this would be feasible only if they can prove that there is full support from CAD tools, commercial tools, or design methodology that allows to deal with timing in an automated manner. And that has proved to be a challenge. So in practice, this is very difficult to do, and that's why you don't find much application in the commercial space. So it's not impossible, but it needs to be done. So those ideas are relevant and useful as long as design methodologies dealing with timing are available or are made available. And I guess this answers the question. It's a two-sided answer, depending on which side you want to look at.
Okay, I have a question myself about the bypass clock network paper. To let's say minimize the delay uncertainty in the clock network and the insertion delay, you go full drive overdrive in the bypass transistors, which bypasses the buffers. So my question is, what is the implication of using still the high voltage overdrive at the bypass in terms of the power manager requirement that is needed? Also in the logic that you proposed later on, you need to do a full drive at the head and tail transistor. So what's the implication for the power manager itself having still to require to go up to boost the voltage to nominal value, let's say?
Okay, well, I would say that this really depends on the system that you have. If you have battery, you already have your voltage available. You're going to have the nominal voltage for sure. So I guess that your question is related to those design scenarios where you don't really have a battery.
Right. You have batteries are different, yeah.
Yeah. So you have to boost up the voltage. Well, but in practical cases, certain subsystems still need a much higher voltage. This might be always on. This could be, let's say, analog subsystem. Many times it needs to be near, it cannot be near a threshold. It can be, 0.8 volt. And in that case, you can still leverage the availability of much higher voltage to increase the strength of the pass transistors, to reduce their resistance, or conversely, to reduce their size for a given allowed resistance. So even if you don't have a battery, you still need voltage domains with quite higher voltage. That is not 0.3, right? And in that case, you can still use it. And the good news is that the load that is offered by these pass transistors is purely capacitive. You charge them once and you're done. You don't need to provide any further energy.
Okay, thanks, Massimo. On slide 34, okay, you are mentioning the area overhead that you had from the methodology on slide 34. What is the chip function, chip module that you use for calculating this area overhead, in which are providing the microarchitecture reconfiguration for the pipeline stages and bypassing timing walls?
Okay. Well, first of all, this is an example based on an FFT. And the reason why we chose FFT is actually because it's not very easy to pipeline, right? So you have actually a quite diverse set of paths. You have LUT paths, you have combinational paths that tend to be signal processing like. So you have basically multipliers, adders. You have FIFOs. So we wanted to show that actually the methodology and the benefits are obtained even in architectures that are quite diverse. The second thing that I would like to highlight is that although I didn't present this here, we actually proved this year in a JSSC paper that you can look up through in our website. We have done the same on a microprocessor, and actually repipelining a microprocessor might seem to be very difficult to do, and we proved that that is not true. So if you just repipeline a processor in a conventional manner, you're going to deal with all the hazards that come from the repipelining of the processor itself. Well, actually, there are ways to repipeline processors without touching at all the control flow. One way to do it, which is what we have explored, is to have time interleaving. You basically, this is very easy to do with the methodology that we have come up with. You double the registers, you make them bypassable, then you redistribute, you retime so that they will make the pipe stages balanced. This means that if you bypass the added registers, the processor will run as it was. It's single core operation. If you instead enable, you don't bypass the additional registers, these registers will basically perform computations like a second core. It's essentially the concept of multi-threading, but implemented in a way that is much simpler than usual, okay? And multi-threading, by definition, and time interleaving, by definition, allows the computation to be completely segregated in two different threads. Even cycles, you're going to do processing for thread 1, odd cycles for thread 2, and they will never interfere. So you don't need to change at all the control flow, which means also the whole software stack. You can use this very same compiler and applications. So basically, you get 2 cores instead of 1 at the cost of area overhead due to the additional registers, which is percentage points in typical microcontroller units. Of course, these approaches are unconceivable in very high performance microprocessors like for servers. That doesn't work, right? But as long as you have a logic depth that is not very aggressive, and all IoT processors are like that, then you can actually do that, and you can basically double the throughput at percentage point type of area overhead. And I guess this answers your question.
Okay. Well, the question also was answered in terms of the area overhead in the slide 34. It's calculated for this function that you're showing here.
Yes.
Good. You've shown a very interesting result on, let's say, in scaling analog modules, bias current for the analog modules, and concurrently with the digital function. So my question is on slide 45, where those results are let's say, summarized. My question is, what are the sensor analog modules that you were scaling, the bias current and so on and so forth? That's exactly in this slide 45. Slide 45. So you are scaling the analog. Which are the analog sensor modules that were scaled in this coordinated speed scaling?
Okay, we are actually keeping all of them on, all of them. And the speed, so in terms of power, this is the worst case power. It means that it's accounting for all sensor interfaces being turned on simultaneously. So we are talking about capacitive. So we had basically an external capacitor for proximity sensing, light sensor, as well as an ADC. An ADC to connect an off-chip sensor. So all of this is running. And I can tell you that the speed limiter is the ADC. And this is running down to hertz at low, the minimum power. But if you have power to spend, you can go up to 2.4 megasamples per second, which is, I believe, quite respectable and definitely covers most of the IoT applications.
Okay, so the analog function is less amenable to downscaling because the ADC will start not functioning correctly at very low voltage.
No, it does. So these results, the ADC is we introduced a new ADC architecture.
It's a full custom. It's not off the shelf. Okay.
Yeah.
Okay. It's a flash one with a full custom. Okay. Good.
Yeah. So basically, in 10 seconds, you can imagine that any capacitive type of ADC doesn't work, because if you want to slow down to hertz whenever you don't have any power, but you want to still keep sensing, as you understand, capacitors don't get along with leakage. So if you slow down operation, those ADCs are not suitable. Instead, flash ADCs, at least up to a certain resolution, and then we actually are working on hybrid ADCs, to increase this resolution. You can think of hierarchical flash, right? Where you can lower down the voltage down to 0.3. So all these results are obtained at 0.3 and down to 3.1 nanowatts, powered by a solar cell, no battery whatsoever. Okay,
that's great. Mm-hmm. Well, that's great. We have one last question because we are running over time already. That's the last question. People out there in the YouTube channel watching the streaming. Juan Pablo from the SATEC company here is a designer. He makes the following comment: we know that some minimum energy designs are sometimes impractical due to the local timing variations in CMOS process. Do you work or propose some ways to mitigate those process variations when you are operating at near threshold, let's say 300 millivolts or so? So his question has to do with mitigation of the extreme increase in variability, timing variability, which has to, by the way, be accommodated with when you reconfigure the data paths in the pipelines.
Yeah. So first, let me tell you that typically the type of architectures that are suitable for extremely low voltages tend to have reasonably long logic depth, and architectural reconfiguration can help you do that, right? So at higher voltages, you might actually decide to take advantage of the speed, but at lower voltages, you always have the
Well, it looked like we had an interruption. We are having some problems. We are having problems with audio from the speaker in Singapore. Well, that was the last question.
Sergio, are we connected again?
Dear Massimo, we are back. We are back streaming again. We had an interruption on your reply and your answer when you were talking about, let's say, how to cope with variations, timing variations at near threshold.
Okay, so at ultra low voltages, because of you can always leverage microarchitectural reconfiguration to increase the logic depth at very low voltages, because this will greatly average out the effect of process variations, right? And by the way, at ISO throughput, this also actually minimizes the energy. The other consideration that I would like to make is this. The effect of variations at very low voltages is largely dependent on the type of technology that you're using. I can tell you that whatever we have shown, we have measured at least 15 to 20 dyes to characterize process variations. And in the papers, we will find voltage and temperature variations. We are using here 180 nanometer technologies for a simple reason. If you want to go well below, the microwatt wall, you want to go down to nanowatts, there is no way you can use, a 28 nanometer technology. You need to use lower leakage technologies and low cost. So, of course, you cannot have everything. Getting down to nanowatts costs something. You're not going to be able to run at gigahertz for sure, and you're not going to have very large scale systems. So all comes at a price. Now, having said that, the heterogeneous integration is actually what can enable the best of the two worlds, and we haven't explored, at least in publications yet, but that's a very interesting area to explore, which is, on one hand, you want to have always-on systems or subsystems that still process and sense, even if there is no battery and there is very little power from the harvester. Whenever you have more energy, then if you want to have more sophisticated digital processing with higher density and at higher power, then you can mix and match, and you can have chiplets of, let's say, 180 always on, and then occasionally on 40 or 28 nanometer or 22 nanometer, right? So that's a space that is largely unexplored, and I would encourage all of you actually to explore it. There's plenty of opportunities there, and we are
okay. Very good, Massimo. Very good. Well, thanks very much, Massimo, on behalf of CASSW Society and the local chapter here. Thank you very much for presenting such an interesting, talk. We're looking forward to your next book. Excellent work, and without further ado, a delay, we'll move on to the next speaker, which is Dr. Erik Marinissen from IMEC, Belgium, chief scientist there. So I'll pass the floor to the next, moderator and speaker, Erik from IMEC in Belgium. Thanks very much, Massimo. Stay safe, and we'll be seeing each other soon, hopefully here in Brazil. Bye-bye.
Yeah, see you all.
Good morning, everybody. We are moving to the next talk. No?
Yeah.
Oh, yes, okay. Okay. The next talk will be given by Erik Marinissen, where Erik will talk about 3D test and design for test challenges and solutions. Erik is scientific director at IMEC in Leuven, Belgium. His research covers topics as TSV-based 3D stacked ICs, sub-10 nanometer CMOS technology, silicon photonics, and STT MRAMs. He worked also at NXP Semiconductors and Philips Research Laboratories. He holds an MSc degree in computing science and a PhD engineering degree in software technology. He is author of several papers and patents and is very active and served as editor-in-chief of IEEE standard 1500 TM in 2005 on embedded card test access, and as founder and chair, and currently is vice chair of IEEE standard on 1838 TM 2019. He is also very active in the organization of several workshops and conferences. He serves on the editorial boards of IEEE Design and Test and Journal of Electronic Testing, Theory and Applications. Marinissen was announced by the IEEE International Test Conference, the ITC, as the most cited author of ITC papers over the 20-year period from 1995 to 2019. This is very impressive. And he holds also several best paper awards. He's fellow of IEEE, he's Golden Core member of IEEE Computer Society, and serves as elect member of the IEEE Computer Society's Board of Governors from the term 2019 to 2021. Erik, it's a pleasure to have you in this edition of the workshop. I asked the audience to pose the questions during the talk using the YouTube chat. And now we are ready to Erik. Thank you very much.
Thank you. Thank you for the nice introduction. Yeah, so today I'm going to talk about 3D test and design for test challenges and solutions. Actually, I should get my mouse in the right computer. This is a talk at the Rio Grande do Sul workshop. So I thought I had to show Chimarrão also to show that I'm in the good spirit here for talking to my friends in Porto Alegre. What I will be talking about, I will actually first start with a short introduction to IMEC. IMEC is a little bit different from university. It's also different from a company. So it's a different kind of organization, and I want to quickly introduce that to you. Then I will talk about multi-die stacks and advanced packages. And then actually we'll go into the meat of the presentation, which is on on 3D test in DFT, where I will talk about wafer probing, design for test, and cost modeling and test flow optimization, all in the scope of 3D chips, right? So that is the meat of the presentation, and then finally we will conclude. Before before we get started, we should put our 3D glasses on then. So sunglasses. I guess it's nice weather in Porto Alegre, and so maybe let's also use the 3D glasses to have a little look at Rio Grande do Sul. So this is actually, the last time I was in Rio Grande do Sul, which is already 19 years ago. So it's maybe too long that I've not been there. And I was also in Porto Alegre, where I have very good memories of the Galpão Crioulo, and there's the football stadium of Inter. Maybe here I offend some people because maybe some of you think it should be Grêmio, but we went to the Inter Stadium. So yeah, this is just my relationship to the south of Brazil, right? Now let's get started. Introduction to IMEC. This is a picture of the headquarters, the main building of IMEC, where on the top floors the CEO sits, etc. I also have an office here on the 7th floor. But yeah, now of course I'm at home because of Corona we're not supposed to be at the office. So IMEC is a world-leading independent R&D and innovation hub. It got started in 1984 as a spin-off from the KU Leuven. So initially maybe we were focused more on processing chips for Belgian universities, but very quickly we focused. IMEC focused itself on companies. So we do a lot of joint R&D with all the major semiconductor companies in the world. We do work in programs where we work with a lot of companies together. We also have bilateral contracts where we just work one-on-one with companies. We do transfer and license spin-offs. We do IC design and manufacturing services. So we work with a lot of customers, and we call them our partners. But they're really customers, so the leading semiconductor companies, the IDMs and fabless. I will show you a list of names in a second. Also system companies. So they are the customers, and we also work a lot with suppliers of equipment, materials, and EDA tools. So yeah, we are very rooted in the industrial world. The headquarters, as I said, are in Leuven, Belgium, but we also have labs in Ghent in Belgium, Eindhoven in the Netherlands, Hsinchu in Taiwan, Bengaluru in India. So the labs are where we have engineers working, and we have sales offices also to be close to our customers in San Francisco, Orlando, Tokyo, Osaka, and Shanghai. So here you have an aerial picture of our campus in Belgium, in Leuven. So you see again this office tower here, and here you see the different fabs. So here we have Fab 1, there's the oldest fab where we process 200mm wafers, and then here we have Fab 2 and Fab 3, and there is 300mm wafers, and Fab 3 was supposed to be 450mm wafers, but as that has not really materialized yet, we're also running 300mm there. So we have actually 3 wafer fabs, and that is one of our main assets. Actually, if you look at the assets, then we think it's the people. 3,500 brilliant minds, as our marketing department calls it, including many industrial residents, so engineers that work for our customers and that are come to IMEC for 1 year, 2 years. So they work just for us in our projects. We also have quite a lot of PhD students and guest researchers. I get my mouse. There you go. So, we also have 3 wafer fabs, which I already showed, so 200, 300, and again 300mm. And then if you look at the financial performance of IMEC, it's amazing growth, and it just keeps on going up. Actually, there was just 1 year where it slowed down a little bit. That was I joined in 2008, and then shortly thereafter the profit went a little bit down, but it just keeps on going up. And actually, most of that money is from industry, right? So 72% we get from working with companies, and there is some regional grant and some European money, but of course it would not make sense for the Belgian or the Flemish government to pay for the research that we do for Samsung or Intel. Why should they, right? So this is actually we just have to do industrial relevant work to make sure that we get our money from paying industrial customers. If you look at the type of topics that we work on, you see here some keywords. So traditionally IMEC was very focused on the scaling of the CMOS, right? So that we still do a lot in that domain. So we're now at 3 nanometer and 2 nanometer process nodes. But of course, as the scaling goes more difficult and we're far at the end of the scaling roadmap, then we also very diversify in doing 3D silicon photonics and all kind of different SCT MRAMs and so all kind of different technologies and applications. Here you see some of our partners. So you see that there's really a who is who in the semiconductor world. So all the big foundries are there, the IDMs are there. So if you look at supplier partners, then there is actually an even larger list. So these are all companies that we have contracts with, that we get prototype tools, beta, alpha, beta versions, and then we debug them together with the supplier, and then so this is how we work with the supplier partners. We have, of course, we have global. Our customers are global, so we also have to have a global presence. So in Belgium are our headquarters in Leuven, then, but we also have quite a sizable lab in the Netherlands, in Eindhoven, but also in the east, right? So in Osaka and Tokyo in Japan, in Shanghai in China, and in Hsinchu in Taiwan, and in Bangalore in India, and then on the east coast and the west coast in Florida and California in the US. If you look at our workforce, that is then of course also very international. So here is actually a plot of the IMEC employees, where they come from, split out of with respect to their home country. Of course, the largest group is the Belgians, because we're in Belgium, so there's many Belgians. The second largest group actually is the Dutch people, so I'm one of them, right? So that is also a big group. But then there's several countries where there's also quite a lot from some countries because they're close to their neighboring countries. Some countries because we have many. Also, our customers come from there, right? So, and actually, if you look at Brazil, here is Brazil. Then we have 19. This varies over time, but at the moment when the slide was made, we had 19 folks from Brazil working at IMEC. So so basically every country in the world almost every country in the world is represented at IMEC, which makes for interesting discussion if there is the world soccer contest, for example. If you look here in the FAB, then I don't know why the video isn't running, but there should be a video of the FAB. I don't know why it doesn't want to run, but so we have a full-fledged terminal with a pilot line. Many of the tools that we have are first-of-a-kind prototype equipment, so the serial number 001 of the supplier, and then we debug them and we get to keep them later on. So, so you can actually make your own virtual 3D visit to our FAB. If you download the IMEC Clean Room on the Google App Store, and you can just walk around, in the way you want to walk around through the different machines and see what they're doing. So that was the introduction to IMEC. Now let's go more technical. So I will start to introduce the multi-die stacks and advanced packages. So actually the CMOS scaling I just talked about continues, but requires increasing investment. It gets more and more expensive to still be on the scaling roadmap, and that means that less companies can afford this. There is now only TSMC, Intel, Samsung, Global Foundries also kind of has stopped on that roadmap. So one day, of course, it will stop also because of technical difficulties. So here you see a picture of the first EUV stepper from ASML, that extreme ultraviolet wafer stepper. That was the first one was in IMEC, because IMEC is then the place where ASML debugs it and makes it work before it goes to their real customers. And so this is then representative for the CMOS scaling. But as the CMOS scaling runs out of steam, the baton is being picked up by assembling packaging. To get advanced packaging, we just put more dies on top of each other, in a single package. with TSVs, maybe true silicon vias that connect the front side to the back side, and that we can make higher stacks. We can put chips on interposers, and so we can go both vertical as well as lateral to make more complex packages, and that then continues for the customer to deliver more performance and low power products, and so Moore's law needs to continue, right? And if it cannot be done just to CMOS scaling, then it goes in another way. So if you look at the three inter-die interconnects, and very well known is the TSV, the true silicon via. It's actually like a super via that connects the front side to the back side of the silicon substrate. Now, actually, it's not really a true silicon via because a wafer is something like 780 micron thick, almost a millimeter thick, right? And these vias are just 50 micron high. So this is 50 micron. So actually, they just go into the surface of the silicon wafer, right? They are not really true silicon via. So we need to thin down the wafer to make them go through. And so that is you don't want to make the TV then too short, because then the wafer can become too thin as well. But 50 micron is doable. And so even though we think that the TSV is actually a very tiny thing just in the surface of the wafer, actually compared to the transistors that are sitting next to it. So here you see the top of a TSV, so this part, and you see the transistors next to it. The transistors are even a lot smaller, right? Because with TSVs we talk in microns, but with transistors, of course, we talk in nanometers. So so TSV is a very big thing for the chip design and the guys in the wafer fab, but it's very small for assembly and packaging. Actually, the TSVs is not what connects the one chip to the other chip. The actual interconnect between the stack dies are the micro bumps. So they're just like solder bumps, let's say. So this is the bottom bump, and this is the top bump that lands on the bottom one. And here you see cross section, and so here we see, for example, this is at 40 micron pitch, where then the copper bump at the bottom is 25 micron diameter. The top bump that lands on is 50 micron diameter, and that is copper nickel tin. Now you see that so here we can make this at a pitch of 10 micron. Here the pitch is 40 micron, so that's a factor of 16 less in density, right? Because 4 times 4 in the x and the y direction, and so that means that there's a lot of pressure to scale down the micro bumps. And so we're already doing 20 micron, 10 micron, and this just continues. So we're making sure that the pitch is not limited by the micro bumps, right? Then so if you look at the interconnect pitch scaling at different dimensions, then you could say in the chip we have, of course, the CMOS or the DRAM circuitry that is nanometer dimensions. But then in order to connect chips, we have TSVs. The TSVs, maybe in 10 micron pitch, right? And we have the micro bumps, now in 40 micron pitch, but they need to go down in pitch, and there's a scaling roadmap for that. Then there is, if you want to get out of the chip to the package substrate, then there is the flip chip bumps. There we maybe talking around 100, 120 micron pitch. And then if you go to the package balls that connect the package to the printed circuit board or something, and we're talking maybe several hundreds of microns of pitch. So the micro bumps are really small, right? Here you see the micro bumps. They're small compared to the flip chip bumps, and they're again small compared to the package balls. So it's just a big fan out or fan in. In order to get from the outside world, which is quite large, into the chip, you need to every time zoom in or zoom out if you come out. There's 3 in 3D stacking. There's 3 stacking approaches. You can, of course, stack dies on dies. So then you first singulate the dies, and then you stack individual dies on individual other dies. Then it's not a very industrial operation. It's largely a manual operation, but it's for IMEC it's good for getting quick R&D results. And so you can also make sure that you stack only dies that, if you first test them, that you only stack the dies that have passed the test, right? So that then you have some kind of a guarantee that maybe the results will also be working. There's also, of course, die to wafer. So then that you use the wafer as a substrate. The bottom die sits still in the wafer, and the top dies are already singulated out, and then we can do automatic pick and place. So we have pick and place machines that put the dies on the bottom wafer, and then actually the stacking, the bonding is a thermal compression operation. So it needs some time, it needs some higher temperature, it needs some force, and so then you especially because it needs some time, you can do this for all these dies collectively, right? So that is also you amortize then the bonding time per die, and that of course is good for the overall throughput time. And also here you can stack only dies that have passed the pre-bond test, right? Because you can actually, if there's a die on the bottom wafer that was not okay, then you can just skip it. Maybe you see that some empty spots, maybe there was a failing die in the bottom wafer, and also the die that you stack on top of them. If they don't pass the test, you just don't stack them, right? So that is good, because that is actually a problem with the wafer to wafer. If you just stack two wafers on top of each other, that is, the positive point about it is that you have the highest throughput, and of course the highest alignment accuracy, because the misalignment is then amortized over all these dies in the wafer. But the dies need to be of the same size, so otherwise, of course, it doesn't work, right? So, and you can also not avoid to stack bad dies on other bad dies, right? So, or bad dies on good dies. So there's always some bad dies in a wafer, and so you can maybe do it wafer matching. So you can try to look at the wafer map and then try to stack two wafers on top of each other, where the wafer maps have the highest still set of good dies, right? But still the compound yield of this wafer to wafer dies is kind of low. But for example, for memories, wafer to wafer is a good thing, because memories you can often repair them. You have spare rows and columns, and then the yield after repair is quite high. And of course the memories also they have an identical size, right? So actually the requirement of the size and the yield, that is actually not a problem for memories, and so they're often wafer to wafer. If you look at the benefits then of multi-die stacks compared to one monolithic IC, so then so you can do heterogeneous integration, right? You can combine different process technologies. And we optimize for digital logic, for memory, for analog, in one product, because you just stack these wafers from different technologies together. You can make a high density and high bandwidth interconnects at low power. Of course, the inter-die connections go through fine pitch microbumps, TSVs, interposer wires. They're much faster and much less power hungry than off-chip communication or going to another chip. So this is more like on-chip communication. So that saves a lot of power and energy, and then you can get high component yields. So for example, here is an example of a Xilinx FPGA that was one of the first 3D chips, and so they wanted to have one big FPGA of 6 square centimeters. So at that moment, a very leading edge technology, which then would mean that the yields would be not very high, actually quite low. And so they have partitioned this one large die of 6 square centimeter into 4 dies of 1.5 square centimeter, and then they test them first, and then only stack the good ones, and then of course the yield is a lot higher for these smaller dies, and so that is then a benefit, getting just to partitioning large dies into smaller ones, and then optimizing the yield, and therefore minimizing the cost. That is a benefit that only can be realized when you do testing, right? So that means that you have to test the dies prior to stacking, so-called notable die testing. So you only stack the dies that have passed the test. And so this is a benefit of 3D stack, multi-die stacks, that only can be realized if you do the proper testing, right? Now some examples of 3D test chips and actual products. So I started with a test chip that we made at IMEC. This was a test chip, no special functionality, we just to test out the technology, where we were stacking 6 dies on top of each other. So there's six dies, and they all need to be interconnected, right? So here you see the cross section where the TVs are. This actually is already from 2012, I believe the date is on this picture. Now this is then the Xilinx FPGA. That was the first 3D FPGA, but actually it's not really 3D because those chips are next to each other. They're not on top of each other, but they're on top of what we then call an interposer. That is another chip, maybe a somewhat older technology that doesn't contain any active material. It's just passive, just interconnects, and that makes sure that that the different parts of the partitioned FPGA can communicate at low power and high speed. So this was actually, sometimes that is called 2.5D because it's not really 3D. It's so people use 2.5D for that, and then so Xilinx was the first one with a product, and so here you see also you see the two stacked chips, you see the micro bumps in between here, and here you see the package bumps. This is the package substrate, and so here you see also this the different dimensions from micro bumps to package bumps in action. Then so real 3D chip was actually from AMD. This was AMD had a product for the graphical processor chip for the gamer market, and so this was the previous product. Are now in 290, and then they came with a new product. And actually, the green dies are memories, and the red die is the logic processors from AMD. And so they could reduce the footprint because you see that the new product is significantly smaller in area. Even though the red chip, the processor that AMD could make, has more area, right? But they achieve this by stacking these memories on top of each other. So we get now stacks of memories, so-called high bandwidth memory. And so here we have still the graphical processor unit, but so there's actually the AMD designers had more memory for themselves, and so they could make a faster chip because if they have more area, they can make the chip faster, and still the footprint for the consumer is smaller. So this is a clear benefit. And then so here again is an IMEC test chip, which we call the full P. So this is fan-out wafer level packaging. This actually is again some technology demonstrated. Where you see that we made quite a complex architecture, right? Here are 7 dies that are connected, and not just in one single tower, but in a more difficult fashion. And I will talk about it a little bit later as well. So if you look at also press clippings, then you see that there's a lot of attention for this topic. Intel is doing the Foveros, so Intel is also quite active in this. TSMC is active in it. Samsung, all the big players are either have already products out or are working on products out, or so this is a hot topic in the industry. If you look at testing of these multi-die stacks, then actually I consider the following test stages. We have pre-bond testing prior to stacking. So then is before we start stacking, then we have mid-bond test where we then we have incomplete partial stacks. So maybe if the total stack is 3 dies, then in the mid-bond test we have just 2 dies stacked on top of each other, and we want to maybe also test that. And the post-bond test is the same, but now the stack is complete, right? So now we have all the 3 dies, and this is just prior to packaging. And the final test is testing the complete stack, when it's packaged. So if you look at the test challenges, then so I will in this presentation I will mainly talk about on one hand test flow optimization, so avoiding too much testing or too late testing. So you can see that here maybe you can do a lot of tests, and so maybe you don't want to do too much testing, right? Because that is just then wasting money in test cost. But you also don't want to test too little or too late, because that might also be quite expensive. And with respect to test access, I will talk about test access external to the die, so or at the stack. So this is if you come from a test agreement, you have to get into the chip, and that is typically through probing or through socket, right? Depending whether you're on the naked dies or packaged die. And so there are some challenges with that. And then once you're inside the chip or inside the stack, you need to get to wherever you want the test to be active. And so then you have to propagate your stimuli and your responses through the die in the stack, and that is where we need DFT for, right? To get the data where we need it inside the die. So so and the external test success, you can see that the first 3 are all with naked die, so you have much more probe technology, wafer probing probably necessary, and of course the final test is only when the chip is in the package, and that is maybe not so different as what we had before. So let's first look at this wafer probing. Yeah, so I will go here over a number of challenges that we have identified that we found in practice also at IMEC while testing our 3D chips, and so we have solved them together with our suppliers, right? So one thing is that we need to handle large tape frames on the wafer probe. So what is a tape frame? Tape frame is actually like a metal ring. You see here in the background the picture where there is a wafer on top of it. So this is a 200 millimeter wafer. And the tape frame, of course, is here you see a photo. The tape frame is of course then larger than the 200 millimeter wafer. So there's a diameter actually of 400 millimeter. There's a standard for that, and that just defines how large this ring is. And on this ring then sits, is spun across the ring is spun a tape, and there you put the wafer on. And we need that to dice the wafers, to dice the chips out of the wafers, but also for ultra thin wafers, for example, that have TSVs in them and that we have tinned. And the wafer becomes very flexible. It's like a sheet of paper that can curl up and down. And so we want to get a carrier for it, and that is then typically a tape frame, right? But if then you want the wafer with the tape frame to go in the probe station, then you need to adapt the probe station. Because in the probe station there's a chuck, right, where the wafer sits on, and so the tape frame is larger than the chuck. So here we had to build some extra supports in blue for the tape frame to hold the weight of the tape frame. But the most important thing probably was that we needed extra maneuver space. So this is something that you cannot do as an afterthought inside the probe station, because you need to, the probe station from the first conception of its design needs to have the maneuver space to make sure that you can move around. And actually there's also here on the side of the chuck sits a camera. That is an upward looking camera that looks at the probe needles, and that moves with the chuck. But yeah, of course, the tape frame, the ring of the tape frame, the metal ring of the tape frame was just in front of the chuck camera. So we had to also reposition the chuck camera. So here we have worked with makers of suppliers of probe stations. For example, Form Factor, actually at the time they were still Cascade Microtech, but now they're called Form Factor, and also Tokyo Electron. So this is actually, they're the two leading probe station suppliers. This one in the engineering market and this one in the high volume production market. So to make sure that they can handle these type of tape frames, right? That was necessary for us. And so the Form Factor can load one tape frame at a time, manual loading through this front port, right? So you just load one tape frame and then you can automatically step over the dies on the tape frame. The Tokyo Electron, because that is for the high volume market, you can even have a cassette that with tape frames, and it loads just the tape frames, up to 25 tape frames by itself from a cassette. So that is one thing that we have solved. And then, if you want to probe on thin wafers or ultra thin wafers on tape frame, so ultra thin I define as 50 micron or less. That of course we need to tin them to have the TSVs exposed. You see, if you have a wafer of 50 micron or less, then you get it behaves like this, right? It's like a sheet of paper. You can bend it. You can actually, if you do this, it doesn't break, right? It still remains working. But so you cannot probe on this, right? You need some support then. So we use then the tape frames actually just as a carrier for that. And but then if you want to probe on it, then you have there's the tape. So the frame itself is a metal frame, but the tape is just some kind of plastic, or I don't know exactly what it's made of. And then the thin wafer sits on top of that, right? And then if you start probing, putting force with a probe needle, then you might have impact on the wafer, on the dies, right? So of course we want with probing good electrical contact and a minimal impact on the other functions of the probe card. So we don't want to have too much damage. So we have looked at different types of probe cards, and here, for example, you see some traditional probe cards which are cantilever probe cards. So they are like this, and they bulldozer out over your probe mark, over your probe path, right? So maybe a trace of 25 micron damage. But so we also have vertical probe cards. They press down vertically. They make a much smaller imprint, and so that is then better. And for ultra thin wafers, we preferably work with vertical low force, MEMS type of probe cards. So they're the most expensive type of probe cards, but you need that to not damage the things that we want to probe. So you see some different probe technologies. So these are traditional cantilever needles, right? So you see different cantilevers. So the probe marker will be this bulldozer path, because it just bulldozers out over the pad. Then we have the pyramid. This is a vertical pyramid. So the probe tips are like this, so they come really straight down. And then we get this type of probe mark. So of course this is a zoom-in picture, but it's a lot smaller than this one. And actually what we have used mainly is the vertical pyramid, rocking beam interposer. That is a very special probe card. So there we get, on micro bumps, we get very small. And you see that the probe mark is actually very small, it's just 6 by 1 micron, and that is actually and there's hardly any damage. And so you want it if you start probing on the micro bumps, because the micro bumps should not be damaged to not mess up the interconnects between the different stacked dies, right? So so another challenge that we have solved is simulated dies or die stacks on tape. So we have maybe just after dicing we have it can also be thin dies. We have dies or die stacks on the wafer. And so if it sits on a tape frame, then you have here you see 4 dies. So this is the cross. This is the dicing street between the dies, right? So the dies are already separated, and this is just here you see 4 dies and the space in between them. So in the center of the wafer chuck, you will have maybe this type of spacing, but at the edge of the wafer chuck, you have the dicing street is larger, because the forces of the tape they stretch at the outside of the wafer chuck. They stretch more, right? There's more force of the tape, and so that means that so that the dies are not nicely in a grid anymore, right? They're a little bit off the grid, because there's difference in probe force. And so another thing that we had is, if you have die-to-die stacks and we want to test them, then we don't want to test them one by one, but we pick and place them in a matrix on a carrier, for example, a tape frame. And so here you see pick and place result of such die-to-die stacks. So on a tape frame, and we do that so that we can test them again by stepping over them, right? Instead of doing one die at a time, one die stack at a time, we can just index step over this with the probe station. But this pick and place is not 100% accurate. And so here you see, for example, a die that it's a little bit rotated, right? So it has a rotation of 1.8 degree, and might also have some misalignment in X and Y direction. And so then we have often on the tape frames we have dies that are not exactly on the grid, right? And then so due to tape stretch or due to pick and place inaccuracy, we have to find out where they are. So then we have implemented an automated misalignment correction by the prober. So the probe station's job, of course, is to land the probes on the probe targets. So on regular wafers, if you just have a normal wafer, you can step with a fixed index size, and so you don't need to worry, because the wafer will be very accurate in that index size. But if you have simulated die stacks on the tape, then we have misalignments in X, Y, Z, and theta, and rotation also. And so with Form Factor, we have worked on auto-correcting the misalignment. So we just take pattern recognition. We take images of the different dies. We found out how much they're off the normal position, and then we can compensate for that. but traditionally, so the probe position is when the wafer is under this probe card here, and then but if you want to look with the camera to the wafer, and there's a plating camera that sits here, right, in the back of the probe station. So every time we had to move back and forth, and that movement would take 6.5 seconds. So just if you want to probe one die, you have 6.5 seconds to move. Then you take the correction image of the wafer. Then you move to the probe position, and you exercise the correction, and just the movement would be 6.5 seconds a single trip, so 13 seconds up and down, and then so that costs a lot of time. So actually, we have also made that we can now record all the misalignments on an entire wafer in one go, and then memorize that, and then do the probing. So that saves 13 seconds per die transportation time. That's of course that's an enormous amount of time. And time is money. So what we also wanted to do, we wanted to probe on micro bumps. So of course the non-bottom dies, they only have micro bumps because they don't have any normal pads anymore. So initially it was thought that it was impossible to probe with conventional probe technology on these micro bumps, because for cantilever, the arrays are too big. With cantilever needles you can only have 2 rows. With vertical probes, vertical probes could not handle the fine pitch, right? So they could not be made at 40 micron pitch. So actually, initially the idea was, either you don't do pre-bond test, but then you will have a low yield. You'll find out that you stack maybe bad dies and good dies, and then you have to throw away the good die as well. We also, what Samsung, for example, did, published this at ISCC 2011. They had dedicated probe pads to not, because they could not probe on the micro bumps, but that also we didn't like. So we said we're going to work out advanced probe technology to probe on the micro bumps. And so we have worked with suppliers of probe technology. And what do we want to probe? So it's actually the micro bumps of 25 and 50 micron diameter at 40 micron pitch, and then also large arrays. So maybe YDO 1 is standard in this domain, so that is 1200 bumps. YDO 2 750 bumps. High bandwidth memory, over 4000 bumps. So really large arrays and very fine pitch. So actually, for quite some time, we have been at IMEC, we have been the world champion in large array fine pitch probing. Was not for working with suppliers. So we work, for example, with form factor on the pyramid probes. There's actually a very advanced probe core. So here you have the probe card, and in the middle sits the probe core, and that is this thing, the metal frame that has 2 thin films, membranes over it, and then here is the tip layer, and then the routing goes to the edge of the core, and there we connect to the printed circuit board. So, here you can also see it. Here you see the probe tips, and then there is this routing layer that is in thin film technology is being designed to, and then we have the connections here, what we call the choreos on the 4 sides that connect to the printed circuit board. So you see the layout where you see the choreos connected, and here you see a SAM picture of the probe tips, right? So these probe tips are very small, 6 by 6 micron, and so this is not a catalog product yet, and actually for the moment the form factor has decided to put it back on hold because they think it's still too advanced for the market. But we also worked, so we had several of these probe cores at IMEC. We also worked with another probe card supplier, Technoprobe. It's the number 2 probe card supplier. Form factor is number 1 probe card supplier worldwide. Technoprobe is from Italy, and they made more traditional vertical probe cards. So you see the top side, you see the bottom side, and then you see in the middle is this thing where you see, and here are the probe tips. So they're just so here you see the probe tips. This is also a YDO 2 array, so 6 by 73 probe tips at 40 micron pitch, and then four banks, right? So 752 probes in total. So that those probe cards also work very well. So and this is a product which you can just buy at Technoprobe, right? So so we have used them on a certain test chip here, we had, this is actually a component of this FOP test chip. We had a true package via design, dies of 2 by 8 square millimeter, where there's YDO2 microbumps, 752 microbumps in 4 banks on both sides of the die, and so they're typically interconnected, like this, and so with TSVs, right? And then so we had the wafers with 3,000 dies on it, and we tested it on our probe station here for microbump probing, and so we had actually all the challenges that I mentioned before. We had simultaneously, so we had probing on large tape frames, ultra thin wafers, singulated dies, dense arrays of microbumps, and we also wanted to do the probe to pet alignment accuracy assessment. And so what I report now on is how we did, what automatic corrections we had to do in Tata XMI, and then what are the probe marks and electrical results. So we could, for example, we could really measure these individual Kelvin TVs, where we then could find out that they had like a resistance of 50 milliohm. So if you look at the wafer map, and you see the theta plotted, and you see the XY translation plotted. So the theta, you see that actually you cannot read it, but they all have the same number, apart from the ones which are colored red or blue, right? So actually, so they all have the same rotation, apart from some that are different. And here you see also that if you see the XY translation, then that is because of the force of the tape, right? So the tape stretches more on the side of the ring. So you see larger arrows than of displacement XY translation. But here there seem to be some dies that are going against the direction of the tape, right? So they're kind of the anomalies. There's also, they correspond to these colored dies here, and this is just the normal tape forces. Actually, if you look at the misalignment that we've measured, then it goes up to the largest misalignment in the Y direction is 500 micron. So you have to think that we're going to probe microbumps that are maybe 25 or 50 micron diameter, but the whole die can be 500 micron displaced, right? And so then we still need to correctly probe on these dies, and actually that works, because here you see a microbump, and you see the probe mark sits here. So we want to probe in the center, but we're just slightly off, right? So this is very good result, and there's then still on dies that have this type of misalignment, right? Because of the forces of the tape frame. And so if the fact that we have 3,000 dies, that if you would have to do the pattern recognition for every die by itself, then it would cost 13 seconds per die, and it would be almost 12 hours, right? So we saved 12 hours test time by just looking at all the misalignments of all the dies in one go and then going there. And so here you see this some electrical results where you see the wafer map results, and again you cannot really read the values, but green means okay and red means bad. And so actually there was this one die here in this particular wafer map that it just wanted to get off the it was kind of taking off from the tape, right? So it was, the tape is some kind of sticky tape, but this particular die wanted to fly off. And so you see that it then tested red, and that is of course what it should be, right? But this is actually, we're very happy with these results. Now let's switch gears and let's talk about the design for test. So now it's more design oriented. So we have developed at IMEC a 3D DFT architecture. If you have, let's say, for example, 3 dies that are stacked on top of each other, and this is more architectural picture, then there might be DFT already in these dies. So we're showing it here with light blue. And then, so what we're going to add in DFT for the 3D DFT is this red rose DFT, and that will basically be requirements is that we want to support pre-bond testing, so we want to be able to either probe on microbumps and then test this die and then all the 3 dies before they're being stacked. But we can also we might probe on dedicated probe pads as well. And so but the 3D DFT architecture is mostly important when when the stack is already there, right? Because then if you want to test, for example, die 3 here at the top, then you need to, you can only access through the package pins then, and you need die 1 and die 2 to work with you to pass on the stimuli, up in the stack and the responses down in the stack, right? So that is, you need cooperative DFT and the different dies to be able to get up and down to the stack with your stimuli and your responses. And you want the test to be a modular test so that you can test the dies, as standalone units. There's not necessarily, will you have one test for the whole stack, and you also want to test the interconnect layers, one by one. So the IMEC architecture actually, has this full that we developed already in 2010, 11, I think. Is based on the IEEE 1500 standard for SoC testing with embedded cores, right? Because you could think that these dies that are in the stack are like embedded dies, it's a little bit similar to an SoC. And so we would leverage the existing DFT features, and what we made is we made serial TAM, a serial test access mechanism that would send in instructions and so low bandwidth data, and we also implemented, so that's like a small country road, one bit per clock cycle, right? There's only 1 bit access, so that's why we call it serial, 1 bit in and out. And then we also have an optional but wider parallel test access mechanism. This is n bits in and out, and n can be user defined. So you can decide to make n0 and not implement it, or you can make n as wide as you want it. And typically you need this parallel mechanism to have more faster testing and high volume production, right? So this is the freeway in Los Angeles. This traffic, of course, would never be handled by a road here, a country road like this, right? So so it's important that the test data goes up and down in the stack, right? So typically we assume that at the bottom of the stack we will connect. There's where the tester connects, and so you need the test data, the stimuli need to be up in the stack. For example, if you want to test die 2, you need to go through die 1 in order to reach die 2. And then the responses of die 2 need to go back down again, the opposite way, right? So in 2010, I used the term test elevators for that. And that is what many people have been using, even though actually if I think about it, test people don't like bidirectional buses and stuff like that. So it's actually more test escalators, right? Maybe test elevators was not exactly the best term. And what we do then is at every die, we give every die a so-called wrapper. So that is actually at the inputs and outputs of the die. So here, this is the functional part of the die, right? We actually put something like boundary scan there. So some flip-flop that you can use to both drive and control and observe the inputs and outputs of the die, and so then we can test the die as a standalone unit, right? So we can shield it off from its environment, from the other dies in the stack, and then just test die 2 in this case. So that is what the wrappers will do. Now the status of IMEC 3D architecture. Originally we developed it for logic on logic, but then we also have extended it for memory on logic, so DRAMs on logic. We have extended it for SoCs, where maybe we have ARM cores or other IP cores and test data compression. We have extended for not just a single tower stack, but also multiple tower stacks, and for making sure that we can do the interconnect, the inter-die interconnect test, that it can be done at speed. And the most recent extension is that we can also do on-chip tolling to mimic real power consumption conditions. So this has been automated by leading EDA suppliers. Actually, we have worked mainly together with Cadence, and we have worked on DFT insertion, automatic test pattern generation, test migration, and this has been incorporated in the TSMC reference flows already in 2012 and 2013. Also, with these companies, we made test chips, and we have made an IMEC in-house demonstrated test chip that was actually with Global Foundries and IMEC together. And we have also made test chips with TSMC to validate these reference flows, right? So this is already quite some time, but then we said, maybe we need to standardize this, right? Because actually the dies might come from different suppliers, And so we then worked on a standard that, standards in IEEE get just a sequence number. So we got a sequence number 1838. That is a standard which actually I started in 2010. We had a study group, and then we started a working group in 2011. Now, I had already my architecture ready, so I thought we'll probably have a standard in 1, max 2 years. But standards are very slow, and everybody wants to say something, and so not everybody wanted to use exactly the IMEC architecture. So it has taken till this year, beginning of March 2020, when the standard was finally released. So there was like 8 years of work in this standard. This is actually a press release from IMEC, where you can see that all kind of captains of industry from Cadence, from Synopsys, from High Silicon are saying that this is a very important standard for them and that they will really use it. So actually when this press release came out from IMEC, so then there's a lot of media that also jumped on top of it. So you get all these press clippings that everywhere in the world where they're saying that the standard is out and it will be very important. Here you have actually some people that were in the working group that helped define the standard. This was at ITC November last year, actually when we heard that the standard was approved, right? So then we're all looking very happy because we know now that the work is from our shoulders. So what is actually 1838? So it specifies mandatory and optional DFT features per die, so that if there's, for example, there's also a wrapper, right? So to test the dies in isolation, there's a serial control mechanism so that you can load in instructions to tell the die what it should do. And then there's also what we call flexible parallel port. That is the multi-bit test access mechanism, right? So this is actually very similar to what I had in the IMEC architecture. And so the standard is then such that if you put multiple compliant dies together, then you get actually an architecture, stack level architecture that should work, and that then you can connect to your tester, and then you can test die 1, 2, or 3. And, so that is actually very similar to what I had in my architecture. If you look at IEEE has actually number of DFT standards, wrapper DFT standards. So there is, for example, boundary scan standard 1500 and now 1838. If you look at those, then boundary scan is actually meant for board level testing, right? So IEEE standard 1149.1. That is, if you have chips on a board, so the board is green, right? Then you can test the interconnects between the boards, and so that just has a serial path, because of course otherwise in the standard you would add package pins. Package pins are considered to be very expensive, and interconnect testing doesn't need too much patterns. So with little test data and just one pin in and one pin out, boundary scan could do the job, right? So, but to then came IEEE 1500. That is embedded cores in a system on chip. There you do not only need to test the interconnects between the cores, but you also need to test the cores themselves, right? Because the chip is just produced when you put the SoC in the factory, and then you still need to test all the cores for manufacturing defects. And so a core, of course, might have a lot more data. So IEEE 1500 needed also, not only a serial mechanism, but also has a parallel mechanism, multi-bit mechanism. And so that is, but it's actually not very well defined, right? It just says you can have it, but the standard doesn't say much about it. So then came 1838. Then we have dies in now we have separate dies that go in a stack. So what here we said, well, we need to test the interconnects, but we also need to test the dies. So that looks like 1500. But in addition, we also need loopback. So for if the left hand side is the bottom of the die, then of course, the stimuli cannot just go from left to right, because you cannot get on the top side of the die, you cannot get out, right? So you need to loop back to get the responses out. So here you have the serial test in, and you have then a serial test out. You have a parallel test in and a parallel test out. So that is maybe specific for 3D, right? Actually, what we also allow here is that these wrappers are not exactly on the boundary of the chip. So you might have some combinational logic, what we call a shore logic, in between. So that is actually necessary to be able to do SP testing. So if you look at the 3 standards in IEEE, then apparently they are being generated every 14 years, because you see there's 14-year intervals between them. Then, yeah, so these are kind of the differences. And 1838, uses some things from 1149.1, uses some things from 1500, and also has some things in Green from itself, right? So, yes, I think I will skip a little bit because here are some more slides on the standard, but so I will skip a little bit the details. I think you got the hang of it. So actually we always consider that the dies in a stack have like a primary interface and a secondary interface. The primary interface is that connects to the tester, and the secondary interface connects into the this is where the primary interface of the next die plugs in, right? So that is what we consider. And so if you could also have, if the tester connects here, then the primary interface and the secondary interface are on the other side, right? Or if you have a 2.5D die stack, then actually the primary and the secondary interface can even be on the same side of the chip, because this is the primary interface and here we have the secondary interface. So this is just terminology to be a little bit implementation independent. And then we have the wrapper cells that are quite similar to what we have seen before. So that is actually being leveraged from IEEE 1500 in the new standard. You can also you can share them with existing wrapper cells. So that is also pretty possible. And so then you can again you can test die 1 or die 2 or die 3 through the serial interface, right? So there's one bit in, one bit out, so it will go a little bit slow. But you can also do it through the parallel interface, and then so then you have more bandwidth, so the testing will go a lot faster. And so likewise, you can also test the interconnects. So the interconnects between the die and its environment, between die 1 and die 2, between die 2 and die 3, through the serial interface, or again through the parallel interface, right? So there's a lot of reconfiguration and mode setting in there, and that is then done with this serial control mechanism. So that actually we have leverage from that is more based on JTAG. So so we have the primary test access port and the secondary test access port, and they plug into each other. And so here you see how that works. That's just based on JTAG, where JTAG, the tap controller, fine state machine. So and you can also have multiple powers, right? So you can have multiple dies stacked them, and then you can just open them or close them as we wish. There's also the flexible parallel port. So the flexible parallel port is the higher bandwidth mechanism. So that is also it's very flexible. You can design a lot of things with it. So, for example, you can change the direction of your test port, right? So you can have in one mode maybe it can be 5 going up and 5 going down, and in another mode there's some others are going up and some others are going down. So you can program a lot with that. I realize that I'm filling my time, but I have maybe 5 more minutes to say something about test cost modeling. So test cost modeling, if you have maybe a die stack of 3 dies, then maybe they come out of 3 different fabs, right? And here you stack die 1 and 2 on top of each other, and then we stack die 3, and then we do packaging, and then we have the customer. So you can of course model the cost for this, but so this maybe assumes perfect yield, right? So we know that there's no perfect yield. So actually, in every step things can go wrong. So maybe you can also have a test after every operation, right? So you can have what we call a pre-bond test after the fab, and so every test you can either pass the good dies and throw away the bad dies in the bin, right? And so then here we have a mid-bond test, here we have a post-bond test, and this is a final test. So if you do all these tests, then maybe you do too much testing, right? Because then maybe the program becomes too expensive just because of all the test costs. But if you do not enough tests, then maybe you're stacking good dies and bad dies on top of each other, and then you find out later that there was one bad die in your stack, and you need to throw away all the good dies as well. So you want to do some integral cost modeling, where you take the cost of the test execution, but also the rejected parts, and you have to amortize that. You have to get it back from the good stacks that in the end you can sell, right? So we have, together with TU Technical University in Delft, we have made a tool called 3D CoStar, where we do some integral cost modeling, where we consider design, wafer processing, assembly, test, packaging, also logistics. If you ship your wafers or your dies from one place to another place, that also might have negative impact on yield, and it has cost. So there is a yield per step in all these operations, and also test yield. Test can also be not perfect, right? There's actually test escapes, and so so all these costs are modeled, and then we can do a baseline analysis, and we can sweep multiple parameters along one or two axes as long as they're in lockstep. We can, we can do all kinds of cost analysis, and then once we get out is an estimated test escape rate, so the quality of your test, how much bad devices will still be tested as good, and also the cost per chip stack with a breakdown over dies and operations. So if you see, for example, how that was used, and for example, we for this die we did an analysis where we should probe for pre-bomb testing. So this was two active dies on top of a passive interposer, so 2.5D die stack that we made in IMEC. And so here you see some of the key parameters of the cost. And so we actually looked at three scenarios. Scenario one was in blue, no pre-bomb testing, so just blind stacking of these dies and then hoping and praying that the results will be good. Or extra pads, right? Because to do the pre-bomb testing, or probing on the microbumps. And so the difference here is that here you get extra area for the pads, and so that then of course is costly. And here you need these expensive probe cards, because microbump probing is of course an advanced probe card. So we assume that there were 1,200 microbumps, that we could not afford to have 1,200 probe pads, so we only will do 10% of the microbumps as probe pads. So then we had a test interface of only 120. That would already give 1 extra square millimeter of die area. So there is less dies that come out of your wafer, and the yield is a little bit less. The test time will be 10 times as large, because the interface is just 10 times smaller, right? But here we have an expensive probe card, because this probe card already costs 50 cents per touchdown, right? So if you have a probe card of 50,000 euros, and every touchdown, you can do 100,000 touchdowns, then every touchdown is 50 cents, right? So, so you see then, and here we also assume that there will be a little bit of negative impact on the interconnect yields after probing, because the microbumps may be both damaged. We have never really seen that, but this is a little bit pessimistic scenario. And you can compare these three scenarios, and then the tool then generates this type of numbers, where here we sweep with the die yield and actually the defect density. And so here you get the relative cost per passing stack, and at 100% we put, if you have perfect yield and you don't do any testing, right? So that's 100%. And then the test cost already will be 14.3% of that scenario. And if your yields go bad, then of course your cost goes up, because then you find many more. This is if you don't do pre-bomb tests, you still do post-bomb tests, right? So you still find out in the end that these dies are bad, you have to throw them away, and that gives a lot of extra cost. Now, if you do the extra pre-bomb pads, then it turns out that that the total cost actually goes up quite a bit, and the fraction of that test is of the total cost also goes up quite a bit, right? And that is mainly because of the 10 times the factor 10 test time increase, because we do not afford more pads, and so we get much more test time, and that makes an enormous expensive test. But if you do the microbump probing, then you can see that the total cost actually, of course, if your yield is 100%, then actually all testing is unnecessary. If you know that it's 100%, but you cannot guarantee that. So then we have a little bit extra cost, but you see that pretty soon something like 85% yield. Actually, probing on the microbumps starts to pay off in the total cost, and so this is actually the extra cost for the probing. So you can see this is some kind of analysis that you can do to find out should I use these expensive probe cards or not. We also have looked at all kind of test flows. So actually, if you have more dies, then you have of course more alternatives. The number of tests that you can do grows a lot, and so we have, for example, uses on this fan-out wafer level packaging test chip, where this is the test chip with the 7 dies, right? So you have here. This is how the stack is being made, and so if you look at the stack flow, then we can do pre-build testing. Then after pre-build testing, we put the dies on a carrier wafer. And here testing is not possible. There's nothing to test. Here it doesn't make sense, but here we can do a pre-build test, right? So we can test if this partial stack is already okay. Then we put it in a mold. Then for here there's no accessibility, but here we can test again if the molding has worked well. Then we actually flip it over on the carrier wafer. Then we take the carrier wafer off. And of course, here you can also not test. But after flipping over, we can probe again, and then actually we put the memory dies on top of it, and then we have to flip over again. And so there's a lot of operations where I have no test access, but here I can test again. So you see that during the different stack operations, I do not have always test access. I have to really look at the flow and find out where I have test access. And if you look at how many different test flows that would give, then you get enormous numbers, right? 10 to the power 18, 10 to the power 34. So this is just considering, should I do at every moment? Should I do a test, yes or no? And so that is enormous amounts of tests, and so you need to be smart about it to optimize your test flows. This is actually what I want to say. So in conclusion, I talked about 3D wafer probing feasibility. So we have 40 micron pitch large microbump arrays, even tinned and diced on a tape frame. And we have been able to probe those with these probe cars, and also probing pick and place dies on the carrier. IMEC, we have defined and patented and tested in test chips the 3D DV architecture based on IEEE 1500. Now there is actually, since a few months, there is the IEEE standard out that it would be a worldwide DV standard that I think is actually very similar to what we have done in IMEC, but that is now the standard that people should use. And then the test flow optimization, you need quite some cross-modeling to evaluate the trade-offs. Because at every test moment you can decide, should I test this die or should I not test this die? And you can easily test too much, but also easily test too little, right? Where can you find more? Of course, the standards you can get from IEEE through IEEE Explorer. You have to pay for that unless you have a subscription to standards, then it's for free. And actually, there's also this book from Wiley that is actually quite interesting. Almost 500 pages. And if you use this code, you can get at the Wiley website, you can get 20% discount. If you're an IEEE member, then actually you get 35% discount on all Wiley books. So then that would be a better option for you. Finally, some acknowledgements at IMEC and at our partners. And that's it. Thank you.
Okay, thank you, Erik, for this very interesting talk. We have some questions from the audience. First, Clovis Feigenbaum has a general question about yield. He doesn't specify the technology, but he wants you comment. What's the ratio of good and bad dies in a wafer?
So that varies largely, right? So I know of products in if you have a very old, mature technology and you have very small area size, then the yield can be 99 point something %, right? So then there's actually very many dies that are good and just a very few that are bad. But yeah, if you have if now you have maybe 7 nanometer CMOS technology, so very leading edge technology, and you make big chips in that, 1 square centimeter or larger, then the yield will be a lot less than 50%, right? So then, it depends mainly on the maturity of the technology and on the area size.
Okay. Keeping the subject with yield, I have a question regarding the yield of silicon vias. I suppose, of course, there is a trade-off between the pitch and yield. And if the yield is a problem in silicon vias, my question is if there is some strategy based on tweak with spare vias, for example, to improve yield of silicon interposers.
Yes. So first I have to say that the process and the making of the vias. When we started that, of course, IMEC is a research institute, so we want to be ahead of the industry, right? So we were among the early ones that did that. Initially, this was quite difficult because it's, you go very deep, right? So it's actually, normally in the processing you never go that deep, and so you really need to like drill in not physically drill, but you need to drill a hole and then fill it with copper. So so there's some processing which is called deep reactive ion etching. That's the process that you use to to drill deeper and deeper, and then we make like a hole of 50 micron deep, right? And then we have to fill it with liner to make sure that if later we fill it with copper, that the copper will not get into the silicon wafer, right? Because that would not be good. So there is some liner and barrier that protects the copper from entering into the silicon. So yeah, initially if you have this very thin kind of small mouth and then a very deep hole, then if you fill it with copper, it gets an overhang, right? So it fills at the top and it stops at the top, but then at the bottom you have some voids. So so then you need conformal filling. That is actually very important, and so that has been developed by IMEC, but also by others. So I think now the industry knows quite well how to make a TSV and to fill it properly, right? So the yield initially was quite bad on our TSVs, but I think now we have this process, very well under control. And so normally we make, actually the key parameter for the TSVs is then what we call the aspect ratio. So the ratio between height and diameter. So normally we do 1 to 10, right? So we make 5 micron diameter and 50 micron height. And then so if we can also do aspect ratio 20, but that becomes more expensive than to make, because then the processing takes more time, and that time is money, so that makes it more expensive. So yeah, the aspect ratio is actually is quite important. Now you can, of course, you can make spare TSVs, right? So extra redundant TSVs that you use in case of that the normal TSVs are not working. The problem with the TSVs is if you have a yield, if there is some defect, then often it is not just one TSV that has a problem, but it's like maybe a group of TSVs together, right? And so the TSVs are typically designed in a matrix structure. But so if you have one bad one, then you cannot just use the one next to it, right? So and maybe you need to move away a little bit from the area where the problem is to some TSV that is a little bit outside and that then means that that if you make a detour, then of course you get a longer electrical path, so your signal will be slower, and so that's then you have to, or even in the non-repair case, you have to consider that there might be a repair, and so your timing becomes worse, right? Because you either need to make a long detour or you repair with a spare that maybe is also defective. So that is actually an intrinsic problem that I'm not sure if there's really good solutions for that.
Okay, thank you. We have 2 questions from William Fantinel. The first one is, can you test multiple dies, parallel testing, with the wafer when the wafer is diced, or after the wafer is diced, only one die can be tested at the same time?
Yeah, that's a good question. So it's quite common in common practice to do testing dies in parallel, right? That is the jargon term for that is multi-site testing. So that's the normal term for it. Multi-site testing doesn't mean testing here and in Japan. There's not multi-site later, but multi-sites on a wafer. So it's actually quite common that on a wafer people do 2x2 testing or 4x4 testing, or it's actually very common. Of course, if now you have these diced dies, then you saw that what happens to the tape frame, right? That there's the dicing streak actually doesn't stay the same size, but it gets stretched, and it gets stretched more at the outside ring of the wafer and less at the center of the wafer. So then I think you cannot develop a probe card that would compensate for these differences, right? So I think the one who asked the question is completely right that will kill the multi-site testing. Yes.
The second question is, when using 3D stacking strategy, do you use to test dies using the testability machine inside each die, or you use to concept special dies into the wafer to test a set, a little set of dies, for example?
I'm not sure that I fully got that question.
I suppose that he's asking if you put some testability block inside each die, or if you use some special die near this die to be tested to accomplish the test of the dies.
No, so normally we don't use special dies, right? So it's just we have the material that we have, and we might put, we put DFT inside the dies to bring the test stimuli, where we want to have them inside the die or inside the die stack. But so if there is, the tester can mimic any other functionality that you might need, right? Because you can just fully program, what kind of stimuli you want to get at which clock cycle and what response you expect at which clock cycle. So there will be no need to have another chip inside the tester or something.
Mm-hmm. And the last question is also from William Fantinel. How do you solder the bumps between dies, intra-dies? Which materials you use? You mentioned that is made in high temperature, so he wants to know which materials and how you perform the solder.
So the microbumps that I showed actually are, the bottom microbump is just copper, right? And then the one that lands on top of it is copper nickel tin. So actually there's is copper to begin with, and there's a little layer of nickel, and then the solder is the tin, right? So like when you're soldering at home, it's also tin. So that is what we use.
Okay. I thank you again, Erik, for this very nice contribution to the workshop, and this ends his session. And now we suppose that Professor José Zambuja wants to say some words.
Thank you so much, Erik, for your great talk. This talk concludes our first big session, our day one morning. And I'm adding here events for the afternoon, which is our second session today. So I would like to thank also Massimo for his talk this morning. In the afternoon, we have a talk by José Gabriel Gomes, and later opportunities with Circuits and Systems Society. And then we have at 3:45, that's Brazilian time, GMT -3, the poster session. So this stream, we'll close it in the next 5 to 10 minutes, and then we'll get back to you on the same channel on YouTube at around 1:50. That is in around 1 hour and 40 minutes. So to close this first session, I will just play a video showing that which posters are we presenting at 3:45. So I would again like to thank all of you who participated in this first session and invite you to our later session at 2:00 p.m.